Mhm. Dear colleagues, welcome to the day 2, and I bring my apology for some technical delay. I would suggest not to waste time and start presentation of Andrew Chaves from Brazil. Please try to be strict with time, about 10 minutes, because of some technical delays. And you can ask one question in chat. Dr. Andrew Chaves, please start your presentation now.
Do you hear me?
Yes.
Is that okay?
Yes.
Okay, so let me start then. Okay, so first of all, thank you very much for the opportunity to be here and talking a little bit about my research group in Brazil. So it's called this Nano 2D Lab. It's part of a larger group that is called the Condensed Matter Theory Group of the Universidade Federal do Ceará in Brazil. It's in the northeast of Brazil. So we are a group of like 5 or maybe there are some other professors here that I did not include because they work more on classical problems and colloids and stuff like that. But my part is it's more on light matter interactions and transport properties into the materials. And we are also collaborating with some other groups all over the world. One of the most important collaborations that we have now is with the Condensed Matter Theory group from University of Antwerp in Belgium. But we also have some collaborators in Minnesota and Columbia University. And nowadays we also have some collaborators in Denmark and in Dresden, in Germany. So they normally do the DFT calculations that I'm going to show later on here. So what we are interested in is, in general, the material is this so-called class of 2D materials that started with graphene. That is like I understand that the audience is not like specifically specialized in the topic that I work on. So let me make a little bit of an introduction here. I think it's going to work also for some other participants at least in the Brazilian team. I know that some of them also work on 2D materials. So let me talk a little bit about it. So it started with graphene. It's a layer of carbon atoms that you can extract from the graphite. Graphite would be like a pile of layers like that. But the interaction between the layers, it's a van der Waals interaction. So it's very weak. It's not as strong as the interactions between atoms inside the layer. And then, so the atoms are very strongly bound inside the layer, but you can exfoliate one of these layers like that. And this thing started in 2004, and then they realized that it was possible to do like that. Then they started to do, because graphene is a semi-metal, but then people started to think like, what about semiconductors? Why can't we find, or maybe insulators? Why can't we find insulators or semiconductors and so on with the atomically thin thickness? So then they started to look for, let's say, boron nitride, and then later on they found this transition metal like chalcogenides, and later on, like 2014, it was black phosphorus. And nowadays people are thinking about combining these things and trying to find even more controllable properties for these things. So what I'm going to talk about here is like the understanding of these materials and the control of these materials. That's the main point. And my specific focus would be on these light matter interactions. The idea here is that if you think about it, the light is an electromagnetic field that is oscillating, right? And such an oscillating field, it can transfer energy to electrons. And the way it transfers energies, it's like there are different ways for doing this. So one of these would be like, maybe the light will excite kind of wave of oscillating charges in the material. These would be what we call plasmon, because each wave I can think about the wave in a particle way, right? So then this is what I call here quasi-particle. So the main idea is I have this thing which would be like a wave-like behavior of a collective behavior of electrons and so on. And these I'm going to describe as a quasi-particle. And this allows me to speed up a lot my calculations and make predictions about these materials. So let's say there is this possibility of having like oscillating charges, or we have oscillating nuclei of the atoms. These would be the so-called phonons. And they also couple to the photons of light, and this is what we call a polariton. And then maybe you just excite one electron from the valence states of the atoms, and then now this is a conducting electron, but the overall behavior of the valence electrons will be treated with one left, right? One extracted from it. It will behave like a positive particle, and this is the so-called hole. And now this combination here is called the exciton. So this is also a way of having like light interacting with electrons in a system, right? So these are the kinds of phenomena that we want to understand in these materials. And if we are able to understand that, we are able also to control it and to control the frequency of light that makes that kind of behavior, or the intensity of the behavior. So the most important thing here is to construct a theoretical model for that, because we want to understand and predict this thing in these materials. So that's because if we want to use these things in future technologies, we want to understand and control the frequencies and probabilities. Because let's say if you want a photodetector or a solar cell, you don't want the electrons to be excited by light and then go down in energy again and release the light again, right? So for photodetectors and solar cells, it would be good to have a low emission. But for LEDs, for example, for emitters, like if you want to emit light with the thing, then it's good to have a high probability, right? So we want to, let's see what are the steps towards understanding this problem then. So the first step would be to do this so-called DFT calculation, density functional theory calculation, or more ab initio calculations, because these would be like the first step in understanding any material. So this is like the most fundamental building block. So once you do that, the problem is that this kind of calculation is very expensive. So what we want to do is to understand the physical properties of electrons, of the quantum states in the solid like that. And then we want to start building simpler and simpler models that capture the same thing. You know, so for example, here I know what are the orbitals involved in these things. These are d orbitals of the metal atoms. This is a transition metal dichalcogenide. So you see these orbitals p, s, and so on. This is the composition of the quantum states in the system. So with those, I build a matrix that represents, this is the so-called tight binding matrix. This represents the same idea, like orbitals interacting between atoms. So with this thing, I'm not going to bore you with equations. I'm showing this just like for a display. So see, we can do that and so on. And then in the end, we find an approximate way, which is this like these blue lines here. This method was developed in this paper here, but it's a like well-known method. So that's why I'm citing here. But this is the way we do also. So it's not made by me, that's what I'm saying. But the way we do is exactly the same steps that we follow. But then in the last part of this thing, we approximate these bands, for example, like parabolas, for example, and then we consider the particles. Now, this is the quasi-particle thing. This is like a particle that is free, but it's not exactly an electron. It's more like a collective behavior that behaves like a particle. And this particle will be Schrödinger equation. If I just solve Schrödinger equation properly with the proper fields or with the proper external parameters and so on, I'm able to understand the system and predict what is going to happen in the system. And now I can also say like, well, let's say that I want to make it more, the light emission more intense, then I can try different fields, different electric environments and stuff like that. That's the goal of my research in general. So these materials, you see that they cover a wide range of frequencies. These are the energies of frequencies of light, but here it's written in terms of energy. You can just convert multiplying by the Planck constant. So we have 2D materials in every frequency you can see here, from infrared to almost violet and a little bit beyond, right? And the stars here are my calculations trying to understand the materials. See that some of them are not really perfect, but it's more or less okay. So another way of controlling these things that we now know that works is alloying. So you start like removing some atoms and putting some other atoms in replacement. In the end, you can find this band gap, which would be like the energy of light that is the lowest energy of light that can be absorbed as a function of the concentration of these impurities that you put there. So I've made a review. If you want, there is a reference down here. You can see this reference there. I have a review of all methods to control the energy of light that will be made by that. So as an example, I have here the case of black phosphorus. So you see that here I can control the frequencies that are absorbed. These peaks are absorption peaks. I can control this by the number of layers. This experiment was made in China, in Fudan University. And there I could see these peaks, and we made a model based on this type binding procedure that I just showed here. And the model are the lines here in the right panel. And the symbols are the experimental data. So you see that we do understand what is happening there. And with these calculations, we could like apply electric fields and then see how to control these energies and so on. So we have now, if you look at this reference, we show there what are the possibilities to control this. So now, as concluding remarks, because now I have only 10 minutes, right? So if you have any question, just ask me later on. But as my concluding remarks, we have different ways of controlling the frequencies, and this is already clear. We know that if we use external fields, mechanical strain, stacking different layers, as I showed for black phosphorus and so on, we can control the frequencies. And this is something good, for example, for solar cells. You see that this is an example of a possibility of solar cell using CDTE. And we have only a range of frequencies here that are allowed for the light to be absorbed. But the light that comes from sun, it comes in several frequencies, right? So if we are able to broaden this range, we would be able to make also better solar cells maybe. But then controlling the efficiency, this is a little bit tricky. Now we are trying to improve this efficiency, like with proximity effects, with metals and so on. But you see that I put this sentence here just as a teaser. You see that, why don't we, if this is a semiconductor that can make a LED of it, why don't we make a screen, a TV screen that is as thin as an atom? We cannot do that because the intensity of light emission, this thing is very low, you know? So if we could improve this intensity, we could make like a very, very thin screen, for example. So this is some of the goals that people are trying to reach in the near future. So with that, I thank you very much for your attention, and I'm open for questions now.
Thank you very much. Thank you very much for your report. Unfortunately, because of no time, probably no time for questions, but questions can be asked directly through the contacts on the website. I would ask you a questions because I read some articles as well about application of Wüstheit by doping for obtaining of solar materials. It is quite interesting, but we don't really have time. So, there is one question. So, if you can ask very fast, so you are trying to control the frequency of emission by using electric field of light. Do you see the question?
Not sure if I can do that without stopping presenting. Let me see. Okay, let's find the chat here. Okay, yeah, so that's the idea. I'm trying to control frequency of emission, but more like frequency, not exactly the intensity yet. So the intensity, it's a little bit tricky, but the frequency, it's okay. You can use electric. But then you asked about the electric field of light. Not exactly. I'm using an external electric field And then with that, I can control what is the frequency of light that can be absorbed, you know? So this is if you apply an electric field, then you can change the behavior of the electrons and the excitons there in the end. So then with that, you control what is the frequency of light that can be absorbed better by the material. That's the idea.
Thank you very much. Thank you very much. Thank you. So
thank you.
Thank you for the presentation. And you can ask other questions through the contacts. So Piotr Lega, the next speaker from Russia, Dr. Piotr Lega, please launch your presentation now.
Dear ladies and gentlemen, do you hear me? Is it okay?
Yes.
Okay, I can start. Yes. Dear ladies and gentlemen, my report titled Factory of the Nanosensors made by the smallest and the fastest shape memory alloy nanotweezers. First of all, I want to introduce my team that works on this project. I am represent the main Institute of Radio Engineering and Electronics, that institute located near Moscow Kremlin. We have BRICS project named Fundamentals for Development of Individual Nano Objects and Nano Devices, Bottom-up Mechanical Integration for Quantum and Non-Local Phenomena Study, Nanoelectronics and Nanobiomedical Diagnostics. Here you can see representatives of 4 BRICS countries: Institute of Nanotech and Nanobionics, China, University of Campinas, Brazil, Indian Institute of Science, Bangalore, and Professor Samnat Khachaturia, Johannesburg. The goal of this project is to create the device or the matrix of devices, the biosensors, and find the possibility to create such devices in mass production that can diagnose infectious diseases in a few seconds. The device that you can see is a field effect transistor, consists of 2 contacts that play a role of source and drain, but the gate plays role virus. The active element is indium phosphide nanowire. This nanowire should be functionalized for specific bacteria, and then measurements need to be achieved. The developed devices provide ultra-high level-free detection sensitivities, 1 femtomolar, for specific DNA sequences measured via the net change in device electrical resistance. Similar levels of ultra-sensitive detection of 6 femtomolar were achieved for Chagas disease protein marker. So Brazil colleagues had provided the possibility indium phosphide nanowire beyond sensor provides this a qualified tool for detection of the chronic infection stage of this disease, leading to improved diagnosis and control of spread. Now we need to produce technology of mass fabrication of feed biosensors to all kinds of infection diseases. Usually in the course of growth, an array of nanowires is formed, for example, in the form of cotton wool or wood grown from the substrate. Nanowires can be of different lengths, widths, and thicknesses and contain various structural defects. In most cases, to create a nanowire-based device, it is very important to choose the highest quality, structurally perfect, and suitable size wire. The device from manuscript had created by manually separated from array. The main disadvantages of this technique are time-consuming, difficulties of selection and replication, and the high cost due to tedious manual operation. For this aim, it is desirable to have a tool that is of similar size as that of the object so as to process it. At this slide, you can see nanotweezers made from composite bimetal material titanium 2 nickel copper with shape memory effect, and another layer is elastic layer. It triggered while heating the material. Here you can see carbon nanotubes grabbing. The key here is composite functional materials B-metal material, pseudoplastically stretched shape memory effect ribbon titanium 2 nickel copper by 1% at the martensitic cold state. And second is elastic layer. What is bending? Bending is compression in the inner side and stretching in the outer side. So we obtain material with reversible shape memory effect, because shape memory effect itself is only one way. Nano tweezers made at the focused ion beam equipment. There are examples of this equipment in our team. This equipment could visualize objects, cut the metal, and deposit material. Here you can see titanium 2 nickel copper ribbon attached to tungsten needle by PT deposition, platinum deposition. Here you can see several steps of the production of the nano tweezers by FIB milling. At the last step, the B-metal structure formed. These shape memory effect nano tweezers are mounted at the needles and easy integrate with the commercial nano manipulators. So this you can see the nano tweezers in the vacuum chamber in the scanning electron ACM, scanning electron microscope. Nano tweezers are open at the initial state, at martensitic state, and closed while heating, while going to austenitic state by current passing. Nano tweezers at the tip of the tungsten needle and heating element as a diode. So this is approximation nano tweezers to the nanowire and capturing nanowire by nano tweezers. The nanowire assembly by shape memory effect nano tweezers. And here you can see the way with these structures. This is biosensor. So please see the video.
Nano tweezers project. The goal of the project is nano tweezers creation. Nano tweezers is a micromechanical device that can manipulate nano-sized objects. We can see on the round table two twin plates. These plates of initial alloy we put inside microscope. The material of the alloy have shape memory effect, a special features of material the same as robot has in the famous cinema. Inside the microscope, that is a manipulation needle. This needle connects with one of a few forms and moves it. The initial plates mentioned by blue color. Let's look how it goes on. The needle is a thin tungsten wire that carefully connects with the plates, then platinum stick them together. After that, nano tweezers tip is sharpened, and then we create a gap with the thin 1 micrometer. Nano tweezers work because of laser heating. Laser also downloads inside the microscope. Platinum heats up till 60 Celsius and compression occurs. When laser is switched off, the plates are unclinched. We use zinc oxide for manipulation because this material has fibrous structure. This width of single whisker is about hundreds nanometers and we cannot see it by eyes. Using nano tweezers, we cut off one whisker and fix it on copper grid. This grid is 3 millimeters size and we move it to electronic microscope for atomic level analysis. Transfer to the customer. The grid with materials reliable fixed on the support and we can move it. The transmission electronic microscope zoomed whisker and showed the monocrystal structure. This whisker is about 500 nanometers in diameter. The next step of the project is studying smaller whisker of other material that has perspective in hydrogen power engineering.
So here you can see experiments on the high-speed response of the nanotweezers. The maximum frequency of nanotweezers working is more than 100 megahertz. Technical characteristic device is follows. Manipulation environment can be vacuum chamber or air. Object dimensions from 10 nanometer to 100 nanometer, and so you can manipulate micron objects. Working temperature from 30 degrees centigrade to 60 degrees. The size of nanotool of the same order with the manipulated object. This is the benefit of the this shape memory effect nanotweezers. So we can create such structures using shape memory effect composite nanotweezers. This is prototype example of the indium phosphide sensor, indium phosphide biosensor. So field effect, the indium phosphide sensor will demonstrate it. Here you can see carbon nanotubes nanostructures created by nanotweezers with single carbon nanotube, thickness less than 30 nanometers. Thank you. We can manipulate everything we can see. Here you can see DNA manipulation. So thank you for attention.
Thank you very much. Unfortunately, we don't have time. I think there are many questions. There would be many questions, but unfortunately, we have to proceed to the next speaker, Dr. Mohit Saraf from India. This presentation has been very impressive, Dr. Petr Lega. Thank you very much.
Thank you.
Yeah, there would be lots of questions, but no time. If we have some time, unfortunately, we are very tight in terms of the time frame. Through the contacts, you can ask questions through the contacts.
Am I audible?
Hello? Hello?
Hello?
Yes, we can
Hello?
hear you.
Okay, so may I start?
Yes, launch presentation, please.
Yeah, okay.
So, Dr. Mohit Saraf from India.
Yeah, hello everyone, thank you. Hello everyone, this is Mohit Saraf from India. Currently, I am a postdoctoral fellow at Indian Institute of Technology, Kanpur. So I'll be talking about some materials for high energy density supercapacitors, and which have been considered as a promising next generation energy storage devices. And I'll be giving some brief, and I'm sure in coming days, one speaker from South Africa will also be delivering some shedding light on it. So as we know that the population as well as economy is currently growing, and because of which all the non-renewable energy sources such as oil, coal, petroleum are continuously depleting, and it is anticipated that in next few decades most of those will be completely depleted, completely disappear. So we have to think about alternatives, and one of the possible solution is to save the energy on demand, on availability, and we can use it later on demand. So when we talk about grid energy storage, so we have a lot of energy storage system, either it is in thermal energy, either in mechanical or electrochemical. So in electrochemical, basically we have supercapacitors and batteries. So I'll be talking about some supercapacitors. So the basic difference between a capacitor and supercapacitor is that in a capacitor you have a dielectric which separates, which differentiates between two metal plates. Wherein supercapacitors, these plates are usually coated with high porous carbon, and they are separated by a very thin separator, maybe in air also. and because of which, and the distance between these two plates is very less, because of which this supercapacitor deliver very high capacitance. So based on their elementary charge storage mechanism, basically supercapacitors are divided into two categories. One is EDLC, that is electrical double layer capacitance, where the absorption of ions is physical. So there is a physical absorption of ion on the electrolyte surface. Wherein pseudocapacitor reversible Faraday paradox reaction takes place, and they store charge. And similarly, batteries and hybrid capacitors or hybrid battery system also involve this Faraday redox reaction phenomena. So as we see this in EDLC type of capacitors, basically you observe ideal capacitive behavior in terms of rectangular CV shape, so CV cyclic voltammetry. So you get one curve in between current and potential, and you get linear charge discharge curve, as you can see from this figure C. Whereas in this Faradic phenomena, which is typical of batteries, you get this peak shaped CV. And in pseudocapacitor, it is somewhat between the situation of EDLC and this battery system. So you don't get ideal peak shaped CV, and it is neither rectangular, it is neither peak shaped. So it is somewhat in between the situation of EDLC and Faraday. So based on this, they have different materials. So whenever we talk about supercapacitors, we talk about energy density and power density. So energy density is nothing but the ability, it's the amount of energy stored per unit volume. Whereas power density is associated with time, that how quickly you can release it. So it is generally represented as a Ragon plot, where you can say it's a very basic Ragon plot just for the general audience. So you can see supercapacitors, they have high power density, and but their energy density, which is on the Y scale, it is quite less than compared to traditional battery system or fuel cells. So ultimately, the goal of our research is to reach up to at this point where not only power density but energy density is also very high. So it has been investigated that energy density primarily depends on specific capacitance, and specific capacitance primarily depends on materials. So if we improve the performance of materials, if we take materials with good properties, then we can improve specific capacitance and ultimately energy density. Besides, supercapacitors are have some other features. For example, they have environment friendly because there is no chemical reaction involved, unlike batteries. They have much faster charge discharge rate, and they can be run over 1,000,000 cycles. So their cycle life is quite high. So supercapacitors have gained some recent practical application. For example, these buses in Shanghai, China, you can see these buses are operating on batteries plus supercapacitor system. So these batteries usually run for a 5-kilometer run, and whenever they are discharged, so they stay at a particular station, and this is a shaft. This shaft gets connected to the terminal, and it gets charged up when the passengers gets boarding, when the passengers are getting on and off the bus. So this is very new technique, and a latest version of this bus was launched in 2015, and it can be charged 100% in 10 seconds. So and it can be run for 5 kilometers. So it is very fascinating that you can charge a bus in 10 seconds and you can run it for 5 or 6 kilometers. And similarly, Tesla, which is a brand nowadays, they are launching this new vehicles based on batteries and supercapacitor system, and supercapacitors here provide them a burst of energy which can be used for rapid charging. And they have associated with the Maxwell technology, which provide them high performance supercapacitors. And today Tesla is celebrating its National Tesla Day. So as I said, the performance of supercapacitor primarily depends on materials. So we have EDLC and pseudocapacitors, and EDLC are primarily involved by these carbon materials, for example, graphene and CNT, whereas in pseudocapacitor, there are metal oxide or conducting polymer. And in hybrid capacitors, we can use a composites, for example, EDLC plus pseudocapacitors. And recently, a lot of new materials have also been introduced, for example, Maxines, which are 2D materials, metal organic frameworks, covalent organic frameworks, and various other materials. And there is always a scope for future advancements. So based on this, different kind of shapes of size and morphologies have also been introduced for boosting up the performance of supercapacitors. For example, if you see in geo-dimension materials, we usually have nanoparticles or coarse nanoparticles. In 1D nanostructures, we use nanowires, nanotubes, nanofillers of various dimensions. In 2D, which have recently gained wide attention, so they primarily involve graphene, metal oxide or hydroxide, transition metal, chalcogenides, maxine, and their homo and heterostructures, and some other 2D materials have also been employed for supercapacitors. So when we prepare our material, we select material. So we, before going for practical application, we do it their lab testing. So in my PhD, I developed various materials. So you can see one of them is РГУ-Fe2O3. So this in РГУ-Fe2O3 we synthesize by various very simple method, in which first we reduce FeCl3 into FeOS3, and then we reduce it by hydrogen under microwave irradiation, and we get this beautiful morphology of РГУ-Fe2O3. You can see small particles of Fe2O3 nanoparticles, which are properly embedded within graphene sheets. So such kind of arrangement is quite beneficial for electrochemical applications. And this is PXRD, powder X-ray diffraction technique. And this is a pattern where you can see all the peaks can be indexed with a standard JCPDS card. So these characterization techniques, they confirm that yes, composite formation has taken place, and now you can go for supercapacitor testing. So we can test it by various techniques. I'm showing you here CV and cyclic voltammetry and charge discharge curve. You can see from first two figures. This is the current versus potential, and you can see a massive improvement in РГУ-Fe2O3 based electrodes over РГУ based electrodes. So you can see red color graph. So it is showing quite a rectangular behavior, as well as its charge propagation and integrated area is much higher than only РГУ based electrodes. And when we perform the same experiment at different scan rates, so its shape is maintained. So we can say it is giving high rate performance. And similarly, we confirm this test by charge discharge test also. So this is charging and this is discharging. So in case of composite, you can see it exhibits high charging and discharging time. So based on this, we calculate specific capacitance of a supercapacitors, and when we plot it with respect to current density, we apply current density and we obtain specific capacitance. So at a particular current density here, you can see at 2 ampere per gram, this composite is exhibiting around 577 farad per gram, and РГУ is exhibiting only 100 farad per gram. So that means there is synergy between Fe2O3 and РГУ, which leads to a massive improvement in the specific capacitance. Similarly, we perform various other materials, including this MOF РГУ systems. So these MOF crystals were grew in a very simple slow diffusion reaction by copper nitrate and transic acid, and then we mix it with by ultrasonation method with the reduced graphene oxide. And you can see from the SCM, scanning electron microscopy image, that two type of structures were observed. In background, you can see large crystal of copper MOF and these graphitic agglomerates of РГУ. And this XRD of copper MOF РГУ composite, you can see the crystal, this XRD pattern of copper MOF was also alike. So it says that on introducing РГУ, the crystal structure of copper MOF is maintained. So it has not destroyed the crystal structure of copper MOF, which is very beneficial for a composite.
Вы отправили, если
we perform this supercapacitor test, and you can see a massive improvement in the charge propagation as well as integrated area in case of composite. And similarly, we observe this phenomena in charge discharge curve. And when we calculate this specific capacitance, the capacitance of hybrid electrode was much higher than only copper MOF and only РГУ based electrode. So the motto behind showing these results is that we can make a combination. And
Dr. Saraf, sorry, time is very.
Yeah, sir. Last slide.
Yeah. So we don't even have time for questions.
Okay. So since various new materials have been developed and recently 2D materials have gained wide attention, but still there is a scope to employ this green supercapacitors based on various solid waste. We can employ a range of various waste, and we can convert them, we can transform them high performance precursors for supercapacitor materials, and we can expect a better, safer and sustainable world tomorrow if we follow these rules. And it based on clean energy technologies. Finally, I would like to acknowledge BRICS, YSF, DST, as well as other funding agency for benefiting me with providing the fellowships. Thank you.
Thank you very much, Dr. Saraf. Unfortunately, because of very tight time framing, I have to proceed to the next speaker from China, Dr. Hongchu Chen. Thank you very much. Dr. Hongchu Chen, can you hear me?
Yes.
Yeah,
Yes.
you can start your presentation.
Okay.
Start, please. You have only 8-10 minutes maximum overall, because there will be
time is limited.
Yeah, very limited.
Okay. May I start?
Yes, start please. Start please.
Okay. Hello everyone. This is Hongyu Chen from China, and it's my pleasure to be able to attend this conference. Today, I would like to present our recent research about the effect of surface quality on deuterium retention behavior in tungsten. My presentation will cover the following 4 aspects. New fusion energy is one of the energies for achieving green, low carbon, and sustainable development. Nowadays, the performance of plasma-facing components is one of the main issues facing ITER and the future magnetic fusion reactors. Tungsten is regarded as a primary candidate for use as a plasma-facing material in the diverter of the ITER and the demo, because of the favorable physical properties such as high melting temperature, high thermal shock resistance, low sputtering erosion yield, and low fusion retention in radiation environments. However, some shortcomings of tungsten cause a negative influence on its application, such as serious embrittlement problems, high ductile to brittle transition temperature, and low resistance temperature in the reactor environment. Plasma-facing materials have to bear high thermal load, high helium plasma flux, and high energy neutron irradiation. The surface of tungsten will be directly exposed to high energy particles such as hydrogen and helium, leading to bubbles, blisters, handling, and even fuzzes. This irradiation damages, degrades the thermal and mechanical properties of the material surface, shortens the lifetime of components, and ultimately impact the surface and the reliability of fusion reactor. Therefore, it becomes particularly significant to study the radiation damage and hydrogen helium retention behavior of tungsten so as to improve its radiation resistance. In order to improve the radiation resistance of materials, researchers generally tend to place their focus on the radiation behavior of tungsten by designing different composition, structure, organization from the perspective of material science at the present stage. The influence of the mechanical processing on the surface, morphology, and the radiation resistance of tungsten is rarely reported. So, does the surface quality of the material affect the radiation resistance? The research groups of Chow, Nishijima, and Scano respectively studied the helium radiation and the hydrogen isotope radiation of furan and chromium alloys, or tungsten with BCC structure, and they all mentioned that the surface quality would affect the helium or deuterium retention in the material, since that it is necessary to polish the samples before irradiation experiments. Until now, there is no uniform surface toughness standard for tungsten inhalation pre-treatment. Besides, researchers on plasma-facing materials machining is also scarce. So the surface roughness RA of tungsten monoblock is in the East device is only 1.6 micrometers, which are manufactured by AT&M. In our study, in order to investigate the relationship between surface quality and the radiation resistance, tungsten is polished by mechanical processing with different surface morphology and roughness. So after that, SEM is performed to characterize the microstructure of polished samples. The surface morphology and the roughness of samples were observed by white light interferometer. Irradiation environment is conducted by a deuterium implantation under the high energy, low irradiation dose, and subsequent thermal desorption to simulate the fusion reactor environment. Here are the SEM of the surface morphology of W1 and W4. Figure A presents the perceived scratches on the surface of W1 before polishing, while Figure B proves there disappears after several hours low-speed polishing, with the surface tending to flatten out and the surface of the W4 become bright to be seen with the naked eye. Figure 4 shows three-dimensional surface morphology of different tungsten samples after polishing process. Surface morphology of samples tend to flatten out with the increase of the polishing time. The unpolished sample W1 has numerous scratches on the surface, which are obviously visible in Figure 4A, while on the surface of W2 and W3, there are some large and small peaks. After 5 hours polishing, the surface morphology of W4 turns relatively smooth compared with other samples. Figure 5 shows the deuterium thermal desorption spectra for samples from room temperature to 900 Kelvin. Under the same irradiation conditions, a shoulder occurred because between 350 Kelvin and 650 Kelvin in the TDS spectrum of all the tungsten samples. The strength of the shoulder decrease in the improvement of surface quality, meaning a greater radiation resistance. As far as rough workpiece is concerned, it has a larger surface area when exposed to the external environment, thus the total amount of deuterium retention increasing. By contrast, W4 has the best radiation resistance with a small peak in the TDS spectrum, and its total retained deuterium amount is only 3.044, 10 to the power of 18. Here, Figure 6 shows the distributions of damage and iron deposition in tungsten in relation with 5 keV. Figure 7 is enlarged perspective of Figure 5 based on our previous experience. The release of deuterium alternates at the this temperature range are mainly related to the irradiation effects. At this temperature range, there is a small peak in the TDS spectrum of W1, W2, and W3 respectively, but no such a small peak occurs in W4 due to its good surface morphology and roughness. Oh, sorry. And finally, I would like to make a conclusion. Results indicate that the capture and the release of deuterium atoms are assuredly related to the surface morphology and the roughness of the material. Tungsten with high surface quality is less likely to be implanted in radiation defects and therefore has a greater radiation resistance in the case of high energy and low dose of deuterium implantation. In addition, our future experiments with high dose of deuterium ions are still necessary. And this is the brief introduction of our university. And this is a brief introduction of our research center. And here are some of our main detecting instruments and self-made processing equipments. Thank you for your attention.
Dr. Hanyu Chen, thank you for your interesting presentation. It is also very impressive. So the next speaker and final speaker in this block is Dr. Louis Boda from South Africa. Dr. Boda, can you hear me? You can start your presentation, please.
Can you hear me?
Yes, yes.
Okay. Good afternoon. I'm Louis Botha, a student from the Northwest University in South Africa. The study was conducted using densional functional theory to calculate water and hydrogen absorption onto bimetallic surfaces. The presentation consists of 3 parts. The increasing environmental pollution is killing the coral reefs, not only in South Africa, but oceans across the world. In order to move away from fossil fuels and lessen the production of greenhouse gases, clean energy sources are required. From the results of the theoretical research, the design and application of a platinum-nickel bimetal as a possible electrocatalyst for use in fuel cells and electrolyzers are discussed. Greenhouse gases are mainly produced by the production of electricity, transportation, and from industrial processes. A possible greener solution is hydrogen fuel, since it produces no greenhouse gases and is renewable. However, hydrogen does not exist in nature and has to be produced. A possible way of producing and using hydrogen as a fuel is through the use of electrochemical devices such as electrolyzers and fuel cells. The electrochemical reactions that take place on the anode is the oxygen evolution reaction and the hydrogen oxidation reaction, while the oxygen reduction reaction and the hydrogen evolution reaction takes place on the cathode. However, the oxygen evolution reaction and the oxygen reduction reaction is hindered. These two reactions require high overpotentials, and due to this, the reaction kinetics are slow. In order to lower the overpotential and to increase the reaction rate, a catalyst is required. The aim of the study is to develop cost-effective electrocatalysts for these two reactions. Platinum is a good electrocatalyst towards the oxygen reduction reaction, while nickel oxides are good electrocatalysts for the oxygen reduction reaction. From literature, platinum-nickel nanoparticles have been identified as possible electrocatalysts that can be used for both these reactions. However, the best mixing ratio of platinum and nickel have yet to be determined. The objective was to use molecular modeling to create unique platinum-nickel compositions. Thereafter, the most stable composition and accurate cell size was identified. At the end, the surface and the electronic properties were calculated to describe the application of the platinum-nickel bimetal as potential electrocatalyst for electrolyzers and fuel cells. Within this model, the site occupancy disorder program was used to create bimetallic unit cells. The smaller cell was optimized using the Vienna ab initio simulation program as indicated. Due to the large number of atoms in the large cell, the general utility lattice program was used along with Sutton and Chen interatomic potentials. Furthermore, Material Studio software was used to create bimetallic slabs from the larger cells. The bimetallic slab optimization, the electronic properties, and the absorption properties were calculated from the settings shown. Using the small cell, the mixing thermodynamics was calculated to determine the most stable slab to be that of the 1-to-1 ratio, or 50%, as seen by the red line for the interatomic potentials, which was also confirmed with DFT using that. To determine the optimal size of the cell, the maximum entropy of each of the cell sizes is compared with the entropy of an infinite cell, as shown. It is clear from the results that convergence of the free energy and the entropy of the large cells are slow in comparison to the smaller cells. Also, a complete computational description cannot be obtained using small cells. Since the values of the larger cells is closer to that of the infinite cell, the larger cell was further investigated. To summarize up to this point, 805 unique configurations was identified with SOD. This was narrowed to 153 configurations using mixing thermodynamics for the 50%. Using probability distribution, this number was further narrowed down to 3 configurations, A, B, and C, which occurs at 300 Kelvin. Higher temperatures were not used due to low probability of occurrences. Therefore, the B and C configurations will be used to study electronic properties in terms of the D band. On the far left side, the symmetrical shape indicates non-magnetic properties for the platinum, while magnetic properties was obtained for nickel, as shown by the asymmetric shape. Looking at the bimetallic configurations, we observe that the D band is similar between these configurations with minimal differences, and that these bimetallic configurations are magnetic, as shown by the asymmetrical shape of the D band. I have published this work in the Royal Society of Chemistry for anyone who would like to read more. The B configuration was used to investigate surface reactions. On the far left, unit cell was cleaved into 5 different surfaces, shown on the right by changing the depth of cleavage. The relaxation percentage shows the stability of a surface before and after optimization. From the table, you can see that it's the 1.5 surface termination. The work function of the D-band center was investigated to predict the absorption ability of the bimetallic surfaces. Smaller work function indicates the surface donates electrons. From the work function values, it's clear that the bimetallic surface is more willing to donate electrons than either nickel, but less than platinum. This indicates that an absorbent should bind weaker on the bimetallic surface than on the nickel surface, but stronger on platinum. Looking at the D-band center, stronger bonding will occur between the absorbent and the nickel surface, but weaker on platinum. D-band center of the bimetallic surface is between that of platinum and nickel, which means that the bimetallic surface is more suitable for surface reactions. Hydrogen was absorbed onto the 0.5 surface termination on the FCC side, while it was increased on the right-hand side. The results shows the first 3 hydrogen atoms on the bimetallic surface have the same trend as that of pure platinum, which changed with the addition of the 4th hydrogen atom to adopt a similar trend to that of the pure nickel surface. An isolated single water molecule was validated before absorption. As seen from the values in the table, the model is sufficient for absorption investigations. A single water molecule was absorbed in a flat orientation onto the bimetallic surface. From table 4, it was observed that the angle and the bond lengths increased as compared to the dimensions of the isolated water molecule, indicating dissociation. The movement of the electrons between the bimetallic surface and that of the absorbed water molecule is calculated using Millikan charges. It's indicated in this figure. If we look at the Millikan charges of the water molecule and the surface, we observe that the hydrogen atoms in the water molecules, Millikan charges, decreases from 0.52 to 0.42, and that the oxygen becomes less negative. This indicates that the electrons are moving from the oxygen to the hydrogen. If we compare the pristine surface with the surface after absorption, we observe that electrons moved around the surface. This indicates that the surface accepts electrons from the water molecule, leading to absorption of the water molecule on the surface, thus chemabsorption. To conclude, there were unique configurations was obtained using SOD. The 1-to-1 ratio was the most stable using Nixon thermodynamics. The cell used was large enough to actually describe electronic properties. The bimetallic surfaces were magnetic, and that the bimetallic surface is more ideal for surface reactions than either the two parent metals. The absorption results shown that the bond strength of an absorbed hydrogen on the bimetallic surface was between platinum and nickel. And for a single water molecule, decomposition of the water molecule was observed on the bimetallic surface, confirmed by elongation of the hydrogen-oxygen bond.
Sorry for interrupting you,
That's it.
Miss Lewis Botha. The time is over, and
yeah, I know.
The coffee break is about to start in a few seconds. That's why I apologize for interrupting you.
Oh no, that was the last sentence.
Yeah, that's great. That's great. I tried to be very strict in time framing. So we have we have 15 minutes coffee break, and I remember you that you can chat privately, or you can search for contacts on the website and communicate, asking some questions. Unfortunately, there was no time here due to some very strict restrictions and time framing. Okay, the next round of presentations will start in 15 minutes. Thank you for all of your reports. They've been very interesting and impressive. Thank you very much. See you in 15 minutes. Dear colleagues, welcome to the next part of our today's forum. And the next speaker is Leandro Malart Moreira from Brazil. Please start your presentation. Hello, Dr. Malart. Can you hear me?
Okay. Okay. Yeah. Can you hear me?
Yes, yes, I can hear you.
Okay.
Hello. Please start.
Okay. So, yeah. So, first of all, thanks for the invitation to be here. So, I would like to show like what we are doing in our research group. So I hope that we can find some good collaborations for future projects. So my main theme is about optical properties of two-dimensional materials. Okay, so I am going to show what we are doing the last few years. So the title is this Imaging 2D Materials with Nonlinear Optics. So before I start, just would like to show where I am from. So this is Brazil. So this is the Minas Gerais state, and this is Belo Horizonte, which is the capital of Minas Gerais. So is the city here. We are in the middle of some mountains regions in Brazil. So we are far from the beach, from the ocean, but we have a lot of mountains. We can do some outdoor activities. So this is our university. So it's the Federal University of Minas Gerais. So we have about 30,000 undergrads and 15,000 graduate students. So this is right here is the physics department. Okay, so the campus is in a nice area, so a lot of green area around. There is a football stadium here and a park over there. Okay, so I would say that I worked with the light matter interactions. So to understand this is basically we have an incident light. It goes to inside the material, which then the light interacts with the material. And then we have for example, the refracted light from this from this prism here. Okay. With this, by studying the refracted light, for example, I can infer what's the material property. Okay. And this can be done in different types of measurements. We can study absorption, we can study photoluminescence, we can study Raman scattering. And today I'm going to show what we are doing with second harmonic generation and forward mixing and stimulated Raman scattering. Okay, so as I said, we are working mainly with two-dimensional materials. So nowadays there is different classes of this type of materials. So what they have in common is that they are very thin. Okay, so it's one atom thin or at least a few atom thin. So for example, we have HBN, which is an insulator, and we have MOS32 and tungsten diselenide, for example, which are semiconductors. And then we have graphene, which was the first two-dimensional material discovered. We have different type of superconducting materials, other type of semiconductors like black phosphorus here, for example. Okay, so we have different classes nowadays. So we have some rich material science here for our research. And so today I'm going to talk about this nonlinear optics effect, just to introduce what does it mean. So basically, when we have an incident light on your material, the electric field of the light is going to induce a polarization inside of material. Okay, and if this induced polarization is linear with the incident electric field, so we are in the linear regime. But if it's not linear, then we are what we call the nonlinear regime. Okay, it can go up with the E square, the electric field square, or electric field, and so on. Okay. For instance, if you just take this second order part here, which we have the E square, we have for example, the second harmonic generation. Okay. In this case, we have the interaction of two photons with energy omega, okay, and then the material converts these two photons into only one photon, but with the twice of the energy. So, for example, if we excite a nonlinear crystal, okay, with a laser in the infrared wavelength at 800, and then with the second harmonic, we're going to see a light coming out with 400 nanometers, okay? And this is very interesting because this Chi2 here is in fact, it's a tensor, okay? For example, it depends on the symmetry of the crystal. So if the crystal has an inversion symmetry, this Chi2 is 0, okay? And also how the polarization of the electric field depends with the induced polarization will depend on this type of Chi2, which depends on the type of symmetries that we have in the crystal. Okay, so our main goal is to probe crystal symmetries, probe crystal directions, probe defects. Okay, and for this thing we need to develop the technique that it requires no difficult sample preparation. Okay, we cannot damage the sample. Okay. And we need to be fast, okay? So with this, we could put this type of technique inside an industry, for example, to check what's the material quality and so on, okay? So in the first example here, I show this is the MOS2, okay? This is a single layer of MOS2. This is a bilayer of sorry. This is a bilayer of MOS2. This is 3 layers. Okay, so this is the AFM image, atomic force microscopy image. So this is 1 layer, 2 layers, 3 layers, and 2 layers. Okay, and this is the second harmonic image. So we can see that for the monolayer part, we have a very strong second harmonic, and for the 2 layer part, we have no second harmonic, and 3 layers, we have second harmonic again. Okay, so if you look at the crystal, the MOS2 crystal, we see that when we have a bilayer, okay, we have an inversion symmetry operation that it's just in between the layers. So in this case, the Chi2 is 0, so we don't see any second harmonic. We only see for odd number of layers, so 1 layer and 3 layers in this case. Okay. What else we can do? We can fix a polarizer in front of the detector, okay, and then we rotate the sample. And what we see is that the polarization of the second harmonic changes, the intensity of the second harmonic changes like this, okay. So we give this 6-fold pattern, okay. We can calculate why this happens, and this basically tells us that the symmetry of the crystal is this hexagonal pattern. Okay, you have molybdenum here and so forth. And moreover, what we can say is we can determine the crystal direction by doing this type of experiment. We know that this is going to be the armchair direction of the crystal, and this is the zigzag direction. Okay, so this is the armchair direction. This one, the X direction, and the Y direction is the zigzag direction. Okay. So now we have a tool that we can determine what's the orientation angle of the sample, okay? Nowadays, this is being used for creating these twisted layers of different 2D materials. So we want to put materials on top of each other with a determined crystal orientation between them, okay? So we can do second harmonic in one sample, determine what's the crystal orientation, do them in the other one, and then rotate one with respect with the other. Okay. So here I'm showing that we can also probe defects. Okay, so this is a second harmonic image, what we call a bright field second harmonic image. So this is a sample that was grown by chemical vapor deposition. So this type of samples, they generate a lot of grain boundaries. Okay, so we have different crystal orientations. So we have this type of disorder, and between the crystals we have a grain boundary here that doesn't generate second harmonic. Okay, but then if you do what we call a dark field second harmonic, okay. For more details, please look at this paper, or we can talk later. Then we can review where are the grain boundaries. Okay, So by doing this type of measurement, we reveal the type of defects that we have and the amount of defects. Okay, you can see the edges and the grain boundaries of the crystal. Okay, so this is different examples for different 2D materials. So this is molybdenum diselenide, molybdenum disulfide, and tungsten disulfide. Okay, so with all of them, we can see locate the defects, all the grain boundaries in the crystals. We also studied the defects in hexagonal boron nitride by second harmonic generation. Okay, so we could also see that we have a strong second harmonic emission from this defective hexagonal boron nitride, and this is a pristine hexagonal boron nitride with a very low concentration of defects. So by comparing these two types of images, what we can see is that the defective boron nitride emits much more second harmonic. Okay, it's 1 order of magnitude more second harmonic than on the samples with a low defect concentration. Okay, we don't know exactly what's the reason for that. Okay, so it can be that the second harmonic is in resonance with the defect state on the boron nitride. So we try to compare with the photoluminescence from these defects. Okay, so we have some tentative explanations, but it's we don't have a complete answer for this. Okay. So what else we are doing right now is doing this vibrational microscopy. Okay. I don't know if everyone is aware about what's Raman spectroscopy. Okay. But with Raman spectroscopy, what we probe is the vibrational of the molecules of the crystals, for example. Okay, so if suppose that we have this type of molecule here with two different atoms, so they are vibrating. So with by doing Raman spectroscopy, we can know the energy of this vibration. Okay, so because we know the energy of this type of vibration, this is like a fingerprint for different molecules and salts. We can differentiate different types of molecules. Okay. However, this technique is very time consuming. Okay. So to overcome this, in the last decade, there are a lot of efforts for doing coherent anti-Stokes Raman and stimulated Raman. Okay. So today I'm going to show some results that we have on stimulated Raman. Okay. So in this case, we use 2 laser beams. Okay, where the difference of the energy of the lasers it equals to this vibrational energy of the molecule. Okay, so when this happens, the Raman signal, okay.
Sorry, Dr. Mallard, for interrupting. 2 minutes.
Sure.
1 minute.
All right.
1 minute.
Okay, thank you. I will be. So we use this microscopy technique to image hexagonal boron nitride. So these are thin layers of hexagonal boron nitride. This is the stimulated Raman signal, and this is the optical signal. Okay, so we have a contrast. We can locate the samples. Okay, and right now we are trying to measure the single layer of boron nitride with this technique. Okay. And there's a lot of application in for the biomedicine field. Okay, so this is amyloid plaques. Okay, this is commonly found on Alzheimer's disease. So this is a fluorescence just to show that this is the amyloid plaque, and then when we can map the amyloid plaque with the stimulated Raman scattering. Okay, so this is also useful for biomedicine applications. Okay, with that, I would like to finish. Please, if you have questions or would like to talk about some specific topics, I'm free to chat. Thank you.
Thank you very much, Dr. Mallard. If, dear colleagues, if you have questions, you can privately send them or ask through the contacts. And we have to proceed to our next speaker, Dr. Alexey Kartsev from Russia. Hello? Dr. Kartsev, can you hear me?
Okay, can you hear me now?
Yes, yes. Great.
Okay. Okay, I will start my talk basically on the broad on the broad topic. I will discuss here the condensed matter systems in and out of equilibrium. Basically, this is my mainstream research. I will start from the example of the static DFT calculations. I've been working since a master thesis. This is like an iron mononitride, and that well-known methods where we can predict the phase transition and equilibrium properties of materials like lattice parameters, magnetic moments, and stuff like that. Can be studied as the dynamic stability, charge density distribution, and similar things. That's been published in PCCP recently. The next thing is when we approach the non-equilibrium physics with still static methods, such as a DFT. This is the good example of that, when we have a superstructure of molecules deposited on the substrate, and we ablate that with a laser, and we see some kind of excitation when we try to understand what's going on there. And we discover specifically on the case of tetraparfilene molecular deposit on the metal substrate that there is a strong metal electron vibron coupling between the electrons and vibration of the molecule, and that causes several interesting effects. Specifically, it can select high spin and low spin states via the quantum transport. And there has been published in Nature Communication that can be understood as several vibration of the molecule coupled to the electron subsystem. There are some modes I'm presenting now. The next approach, the next step to approach the non-equilibrium physics is a time-dependent DFT as the most visible method. And the starting point here is study the complication of the physics based on the model systems, which can be both quantum transport and ultra-cold atoms. Mainly, they all based on the Hubbard model, where the Coulomb interaction can be taken account, and external potential can describe external fields or like effect of the ions and things like that. There are interesting things going on right now, and the most simple case which we can deal with is the 1D systems, and this is the example we've been studying of spin separation in 1D cold atoms. We can do it for higher dimension, and there are another interesting things that are going on, and that also can be approached from the DFT point of view plus the mixture of DMFT. This is the example of the 3D fermions trapped in the external potential, and then they open when they open a trap, and we look what's going on, and we let them to evolve in time. So we can do the collision of electronic clouds in 3D and see what the physics is going on there, and other things. It also can be applied for the quantum transport problem, where the atoms' vibration can be taken account on in terms of the model systems. This is well-known Holstein model, which can be studied which can be tackled from the Ehrenfest dynamic. Also can study regimes and other things. Another application of methods of non-equilibrium methods can be used for the new generation of 2D materials. I mean, here's the structure of classical 2D materials like halogenides or graphene, which well studied now. And the new generation of 2D magnets, 2D materials is a 2D magnets. I mean, they've been discovered recently, like 2 or 3 years ago, and now there is a bunch of high-profile publications on the net, and then you see that it's a growing market, basically. And a part of the problems being attacked before, we have to take they have to take into account the magnetism, and the magnetism can be taken into account using the Heisenberg model. The important thing here that those materials exist, because before scientists would assume that they do not exist due to Magman-Wegner theorem, which tells that 2D magnetism does not survive. But apparently it survived because of the anisotropy, and that should be properly taken into account by extended Hamiltonians and models. The work I did, I proved that there is extra terms should be taken into account, namely like biquadratic interaction in 2D magnets, and that's been well agreed with experimental data and been published, is accepted in PG computation material, Nature Scientific Partner, and that's like the key moment in 2D magnets, where higher order exchange is essential part of the picture, basically. And then you can do the Monte Carlo simulation, getting, for example, like magnetic domains and other interesting things, like here the dependence of magnetization as a function of temperature. Right now, we're also working with my colleagues from Livermore and Stanford, writing the code for time-dependent DFT for real materials, optimized for the GPU machines. And the GPU, it's a future of computational physics. You can look on the GitLab code for the name of the code is Inc, so you can download, and you're free to contact me via the official email, private, or the WeChat or the WhatsApp. So basically that's it. Thank you for your attention.
Dr. Kartsev, thank you for your very interesting presentation, actually, and thank you for the saving some time. We have even time for questions, and if everyone has some questions, we can ask Dr. Kartsev. Please type the questions in the chat, or does anyone have questions to Dr. Kartsev? So INQ DFT code is free software. So the question, Dr. Kartsev, there is a question about software. Is it free?
Yeah, it's free. You can go and look on that GitLab, and I mean, you can download. We are just at the beginning because we are writing from the scratch, and I mean, basically the main purpose to optimize as much as possible for the GPU, and you know, GPU is kind of the future in the computational physics, but it's been hard because it's not been settled yet, which the architecture of the GPU processors will be used in the future. But I mean, we're trying our best, and that's in principle should be like much faster than other DFT codes. And the code wrote on a C++, it works like an engine, you know, so it's basically, you can use it as a library inside your own code. That's the advantage. So it's not, it can be used as a separate code, or it can be used as an engine inside your own code written on C++.
Okay, thank you. Any other questions? All right, if no other questions, let's proceed to the next speaker. Thank you, Dr. Kartsev. The next speaker is Dr. Sakshi Chauchan from India. Sorry if I pronounced wrong way.
Okay.
Oh, I can hear you. I can hear you. Please
okay.
start your
Thank you so much. Today, I'm going to present my topic on the biomechanical investigation of extracorporeal irradiation on resected human bone. Unlike other presentations, this is a little bit different in the sense each and everyone was explaining about metal materials, but here we come and we get into the details of human bone. So what this project is about, this is already a collaboration between IIT Delhi and it's All India Institute of Medical Sciences, New Delhi. This is a hospital which helps us to get some human patients which willingly donate some bone parts of themselves so that we can have a testing idea of how they have been therapized using radiations of having bone cancers. So what bone cancer is exactly, since we know in this pandemic also we came across that human health has always been a bigger concern above all. And this bone cancer is actually happening in young adult patients. Like probably I have seen the smallest one of 6 years and it goes on, it goes on. So bone sarcoma, which is also known as bone cancer, is of two types, like Ewing sarcoma and osteosarcoma, mostly prevalent in childs and young adults. And one important thing is that it is third largest in young patients, third largest. So we can understand the extent it is having impact on the young patients. So before 1970s, what was the idea of having bone cancer and then treating it? So treatment only involves one thing, and that is cutting the organ part. They cut the organ part and amputate the patient. That means he has no longer with the organ or bone. Now the question arises how they move, how they just do their daily works. After 1970s, with an advent in technologies, there are certain things which can help these patients and these younger childs. The one of them is bone graft. We take a bone from other patient and just put it, other donor, and put it into the another's body. But this involves too much risk of disease transmissions and all. Another way is prosthesis, where a cut part is replaced by a metal. But when we talk of small childs, they keep on growing. They keep on growing in height. So they need to be replaced in every 5 years or 6 years. So the repetitive surgery is always a big concern. The third is ECRT, which is actually extracorporeal radiation therapy. Now what this ECRT is, it is extracorporeal radiation therapy, where extracorporeal means, for the general public, I can say that it is out of the body, taking the bone out, then radiating it for sterilizing purpose, and then placing it back. So this technology on the whole has a number of cutting edge advantages, like you don't have any disease transmission back from the donor to the recipient. You don't have any resurgeries again and again, because bone, it's a customized bone. It is your own bone placed into your body. So there is no question of disease transmission as well as resurgery, and it is a bit comfortable to the patients. Generally, most of the Asian countries and European countries are following this procedure in bone cancer, but no study has ever thought of what are the impact of this radiation on the patient. So as you can see in the image, so this is the patient with bone cancer in the tibia, and this bone X-ray, this is an extra mass. This is bone taken out from the body. It is scrapped off from the extra mass, and it is sterilized in the radiation chamber, and it is placed back. Okay, you must be seeing this one. Okay, so, and it is placed back into the patient's body with these fixtures. These fixtures, these are needles and these are screws. So ECRT is a complete therapy, but there are certain things which need to be answered and which need to be looked so that we can optimize ECRT to the full level. So the first was, there are so much less studies looked at mechanical, structural and compositional changes due to single heavy dose radiation. There are a number of studies you can find literature available which says 2 gray in 1 week, 2 gray in another week, 2 gray in another third week is okay, no issues. But here we are talking of 50 gray in a single dose. Second is, what are the short-term and long-term clinical outcomes? By clinical outcomes, I mean, is the patient functional or not? Is he able to move, or she is able to move or not? And the third one is the implants I've shown you just before. are only designed for fracture criteria. They are not for this criteria that we place the patient's own bone back. So to deal with all these gaps in the literature, we must answer certain questions. So the first question is, what are the effects on mechanical properties post-irradiation? After irradiation, what are the effects? Second is how the indented surface looks. Third, how much is the change in bone quality? By bone quality, I mean to say, what is the status of bone minerals? What is the status of bone collagens? How is the amide functioning? The fourth one is the question is, how is the organic structure changing within the bone? And the fifth is, what is the status of bone microstructure? All these questions will be one by one answered with the techniques which I mentioned in this slide, that instrumented indentation technique will use for mechanical properties, atomic force microscopy I have used for indented surface, bone for Raman spectroscopy, change in bone quality will help us in this, and amide deconvolution, the first derivative using Raman spectroscopy of the amide band helps in alterations in collagen structure. And the fifth one will be answered by micro-CT. So now the question also arises, why only these techniques when we have bulk testings also, like we can go for UTMs, we can go for micro-indentations, then why only nano-indentation? Because bone is a very, I should say, a heterogeneous or a complicated material. It changes its hierarchy at every scale. And every scale, this material can be tested in a different way or should be tested in a different way. The macro scale cannot be tested like the meso scale. So while looking at the bone growing and healing properties or how the bone is reacting, we must focus at this level, which is mineralized collagen fibrils. And this has to be tested by nano indentation, micro CT, and Raman spectroscopy. So bone is a hierarchical structure which should be tested with different testing parameters on different scales. So these were the patients, unfortunate patients, or I should say the subjects of my studies. You can see here, this is patient number 6, which is 6 years old, a female child, and there is also one 26, a female. So these are all enrolled for the study, and they were willing to help us by giving a small part of their bone, which is already out of their body during operation. So we had this testing, and it is from Ewing sarcoma. Many of the samples were from cortical region, some of from tubercular region, that is a porous bone, and from different locations of long bones, tibias, humerus, femurs we have. One sample we acquired from control sample, and this is of no cancer patient. It is a person who lost his life in accident, and we have the bone of that patient. So now how the study is designed so that we can answer all the questions of ECRT. So this is the complete how the study is designed. The first we have patient suffering from MBT, a long bone like femur, tibia, humerus suffers from cancer. Post-irradiated sample is being taken and one pre-irradiated sample is being taken. The sample is being saved by using ultrasonications and stored at 4 degrees saline water. And the sample is then been processed so that testing can be done by taking a cylinder of epoxy and then embedding the sample. And this sample is then placed for nano indentation, for AFM, for Raman spectroscopy. For micro CT, we have a different sample of the same patient. The study is already been published in Journal of Mechanical Behavior and Biomedical Materials. So how the bone reacts, I'm coming early to the results, that by nano indentation, we acquired results in young modulus is severely decreased. Young modulus of the bone post irradiation is severely decreased, while hardness is also severely decreased. But the dissipation energy increased in all the samples throughout all the patients, from patient 0, which is of control, to patient 15. And mineral content, we can see mineral content is also decreasing. So for patient 0, you can see there is a 1.8 in pre-irradiation sample, while it becomes the ratio of 1.2 in post-irradiation sample. There is a heavy decrease in a mineral content. So while a mineral content is a leading factor why everything is changing, the first thing is when we have a less mineral, we have lesser younger modulus, we have lesser hardness, but we have a higher dissipation energy because now the response is coming from an organic material or collagen, I should say. So what is the mechanism behind? The bone at the mineralized level, I have shown you in the previous slides that it is from one collagen to another collagen, and in the middle we have hydroxy mineral particles. So this is the condition when we have pre-irradiation bone. When it comes to post-irradiation, all the mineral content is lost. So these collagens are now easy for sliding. So this deformation on loading, this gives us deformation on loading since there is no mineral particles in collagen to collagen interface. So bone is a material which responds coherently between function, compositions, and structure. So if any of the one changes, like if function changes, composition will definitely change, structure will definitely change. If composition changes, both the things will change. So under ECRT, it is a very important question that whether we can see after surgery, whether the patients are able to walk or do daily routine jobs. So effect of irradiation on a bone, in a big picture I can say, when a modulus of a bone comes from collagen and mineral particles, when bone goes under 50 gray irradiation, there is a decrease in Young's modulus and hence the load bearing capacity. The bone behaves much on a flexible side. Thank you for your kind attention.
Dr. Chao Chan, thank you very much for a very interesting presentation. This topic is very distant from what I study, but it is very interesting. So we have time for one question. If anyone has questions, please type them to Dr. Chao Chan.
So the first question is, what's the material of AFM tip which was used in indentation? It is titanium.
So the material is titanium.
Right.
Other
it's
questions?
4 nano. Yeah.
Other questions? Any other questions? Or probably they will be sent later through the personal cabinet of the website.
Thank you so much.
Thank you for the presentation. And the next speaker is Dr. Wen Yu from China. Dr. Wen Yu from China. Hello, Dr. Yu. I cannot hear you.
Okay.
Ah, I can hear you now.
Okay. Can you see my PPT, PowerPoint?
Yes, I can see. I can see.
Okay. May I start?
Yes, start please.
Okay. Thank you. Hello, everyone. I'm Wen Yue, a professor from China University of Young Sciences. It's my great honor to stand here to introduce my research results. My research focuses on the coating technology and the super hard materials applied on drilling device. Accordingly, my topic is armors on drilling device. First of all, let me briefly introduce China University of Young Sciences. CUGB was founded in 1952, who was one of national 64 king college and universities, and also the first group of 211 project universities, and one of first classes international university in the field of geosciences. As a researcher work in CUGB, my job is to develop new materials or coating technology so as to improve the performance of drilling rig. Consequently, my research field involves drilling engineering, mechanical tribology, and surface engineering, exploration technique, and super hard materials. So let me introduce the background. Every geologist has a dream that we can drill anywhere we like, in deep earth, in the sea, in the north or south poles, or even in outer space. Fortunately, this dream is becoming reality. To date, Mars drilling, deep sea drilling, Arctic pole drilling, and deep earth drilling with a depth of more than 10 kilometers have already been done. But such extreme operating conditions like high vacuum, ultra-high temperature, the radiation of atom oxygen, and ultraviolet in outer space, hard rocks and complex geological environment, corrosive effect of seawater, marine organism corrosion, and low temperature, and so on, raising higher requirements on performance of drilling rig. In order to cope with various of extreme operating conditions, armors, such like coatings or super hard materials, should be put on drilling rig. So far, we developed friction reduction and anti-wear coating for space drilling, strengthened coating for deep earth drilling, anti-corrosive coatings for marine drilling, and anti-icing coating for polar exploration. Under outer space, this slide shows the under outer space environment. The drilling rig have to be lightweight, so we use titanium to manufacture the drilling rod. Radiation-proof, compact, and powerful enough to dig deep into the surface of outer planet. During the process of drilling, the lower friction and the lower energy consumption, the better wear resistance and the more excellent capability of drilling with friction reduction and anti-wear coating. Friction coefficient of space drilling will be decreased by 30%. And it's very light. So this one was improved 5 times. Meanwhile, the coating makes drilling rig can bear the radiation of atom oxygen and ultraviolet. Through iron nitrogen combined with surface texture composite treatment technology, the wear life will be significantly improved. The active control of its friction and wear performance is realized. As shown in the picture, the marine drilling rig with anti-corrosive coating results in a corrosion potential of -0.5 wattage, a corrosive current density about 4.7 microampere, and a surface hardness of around about 1000 HV, which increased the corrosion resistance life by 3 times. and decrease the energy consumption by 10%. This slide shows the titanium carbon composite ceramic coating is prepared by high velocity oxygen fuel, which significantly improves the wear and corrosive resistance of variable parts of drilling equipment under complex working conditions. The iron basis amorphous coating was provided by cold spraying and thermal spraying respectively, which improved the surface mechanic property and corrosion resistance of workable parts of drilling equipment. Next one is about anti-icing coating. This type of coating on critical parts of polar drilling rig results in a whitening angle of 120 degrees, which gives excellent hydrophobicity and icing resistance, and make the drilling rig is able to work on the limit of working temperature of -40 degrees. This slide shows that PTFE and graphite composite coating is provided by spraying and surface texture treatment technology, which improves the hydrophobic performance of drilling tools, and it can effectively prevent the mud pack phenomenon during the drilling tools operation. Based on above research work, we can develop a series of smart coating put on the deep earth drilling, the accuracy of information transmission system, and underground position system was promoted greatly. Smart coating on drilling rig lets it spin, collect, and pass the underground information so as to get the activity of drilling rig. And we also develop many kinds of super hard materials, such as the diamond tools and cutting tools, just like some thick coating that can use in drilling parts of the drilling tools. It can promote the very excellent anti-wear resistance and drilling capacity. And we also develop many kinds of the drilling rig from the depth 600 to 5 kilometers. Those rigs play a basic role on many national key projects. We also have many science and technology awards. Thank you all. Thank you for your attention.
Dr. Yu, thank you very much. Very interesting presentation. We have time for questions, and if everyone has questions, please type them. Or raise the hand, you can ask the question using video. So the question, do you consider structural changes under high pressure?
Sure. Just like we use a high temperature and high pressure technique to produce the diamond, makes the structure transfer from graphite to diamond structures. So the material should be changed of its structure.
Thank you. So another question, up to which level of pressure?
Oh, yeah. the pressure range from 5 G Pascal to 6.5 G Pascal, and the temperature would be around 1,200 degrees. That will be about 2 hour 2 minutes. It will be make the graphite transfer to the diamond structure.
Thank you. Any other questions? We have some time for other questions, if any. All right. If no questions, let's proceed to the final speaker in this block. Dr. Marin Ksaba from South Africa. The next speaker is Dr. Ksaba. Hello, Dr. Ksaba.
Hi, can you hear me?
Yes, I can hear you. Hello.
Okay.
Please, you can start.
Yes, just a moment.
Yeah, you have time.
Good afternoon, everybody. My name is Morena Klaba, and I'm from the Institute for the Development of Energy for African Sustainability in South Africa. And my talk today is based on carbon spheres for the electrochemical energy storage in high-performance supercapacitors. So first of all, I just want to thank Dr. Mohit Saraf for giving a very brief and thorough introduction. So I will not spend too much time on the introduction. I'll just try to be short due to time constraints.
Actually, sorry, you have time. Now you have time. We have 20 minutes before the next round. So you were lucky, some time was saved.
Thank you very much. I think that comes with the perks of being the last speaker of the day. Okay. So just to give a recap, so there are different types of carbon nanomaterials, and they've got a different physical-chemical properties such as surface areas and porosity, and they can also be tailored for surface chemistry. So they find most applications in catalysis, energy conversion, biomedical, and environmental applications. So the types of materials that we are interested in are the carbon fibers, the films, nanochips, monolithic carbons, and graphene-based materials. What this project was about is the carbon spheres. So we all know that lithium-ion batteries actually have a very high energy densities, and they are used in almost every electronic device. And we can just say, okay, oh, I'm happy, thanks. I'll just use lithium-ion batteries. But then there are some drawbacks based on that, including the surface areas and the fewer Faraday active sites and poor conductivities, etc. And we must not underestimate this field, however, because the 2019 Nobel Prize in Chemistry was awarded to 3 scientists for the development of lithium-ion batteries. So in supercapacitors, what is important is the Ragon plots, which gives the specific power as a function of a specific energy. So we can see on the graph on the left that the electrochemical capacitors actually have a very high specific power compared to lithium-ion batteries, as well as the nickel and other capacitors as well. So the story I actually wanted to make a note about this, that it all started when Michael Faraday in 1861 took a pile of coins and made a pile of it with the zinc sheets and a piece of moistened paper to create a photovoltaic pile, which was able to generate some few volts. And up to today, we are still working on it. So my talk will be based on experimental techniques and methods, characterization, and the energy behavior. Part of the carbon spheres that we made, we used actually the phenyl formaldehyde resin, and we coated it with silica and carbonized it to different temperatures from 500, 600, and 700 degrees Celsius. And the table there shows that just the physicochemical properties, the surface area, the pore volume, and the pore diameters, as well as the particle size. And on the right is just the TEM images of these carbon spheres. Another type of carbon spheres that we prepared was the porous yolk shell structured carbon nanospheres. So in this method, we actually just took the resorcinol formaldehyde resin and then calcined it straight to 700 degrees Celsius to form the solid carbon spheres. And in another route, we actually coated the resorcinol formaldehyde spheres with silica, and then followed by ethyl diamine to actually form the pores, and finally calcining at 700 degrees Celsius. And the TEM images are shown at the bottom, as well as the table for physicochemical properties. And then another method that we used was the polystyrene polyacrylonitrile. So in this method, we actually took the PS pen resin and then assemble it on a flat carbon sheet to actually form the carbon sphere on the surface of the carbon sheet. And you can see also the surface areas were very good. And on the right, we can see the carbon sphere with an inner diameter of 80 nanometers and a shell thickness of 10 nanometers on the surface of the carbon sheet. So we did some different types of characterizations, but due to time, I did not include all the characterization techniques. So the TGA just shows the decomposition of the materials under nitrogen and under air, and we can see the decomposition of the CTAP and ionic liquids at about 260 degrees Celsius, and the nitrogen isotherms showing very good materials that have regular pores and also uniform size distribution. The solid carbon spheres and the hollow carbon spheres on the sheet also showed very regular and uniform pores, as well as size distribution, actually obeying the type 4 isotherm and the hysteresis loop type 3. And we also did XPS characterization on these materials, and we actually saw that from the full scan of these materials, we saw that over 90% was carbon and nitrogen and oxygen with very minute quantities. But then if we deconvolute the peaks for the carbon 1s and the oxygen 1s, as well as the nitrogen 1s, we can see that we don't have we don't have actually one type of material. We have a distribution of different types of bonds within the material itself. We actually did electrochemical tests of these materials, and we can see that for the mesoporous carbons with ionic liquids, we had a quasi-rectangular cyclic voltammograms with very good area, showing that there was a very good supercapacitance storage ability. And we did also GCD, which is charge-discharge measurements, and we can see that there is actually a very good reversibility during charging and discharge. We also measured the materials in 2 electrode system that actually represents a very applicable and industrial scale type application for energy storage. And we can see that as we increase the scanning rate, we actually have an increase in the area of the cyclic voltammogram. And the Nyquist plot where we had actually a very nice semicircle that shows us that there was a very good ion mobility on the surface of the material during charging and discharge. And sorry. We also did some cyclic life stability test, and we were able to retain up to 95.8% after 10,000 cycles. And the insert there just shows the first and the 10,000th cycle after cyclic stability test. These are the electrochemical behaviors of the porous yolk shell carbon nanospheres. And we can see the CV caves are also quasi-rectangular, and the GCD caves are also isosceles triangular, showing a very good charge discharge. Lastly, I just want to also talk about the 2 electrode system for these materials, which actually resembled the materials which were from the previous slides. That was the porous carbon spheres. So the hollow carbon spheres, which were actually immobilized on the sheets, actually showed a very good supercapacitance applications with very good energy storage. And we can see that after 10,000 cycles, 99% was retained. And the insert there showing the first 10 cycles and the last 10 cycles of the 10,000th cycle. So I also just want to mention that in this field, as much as we actually pursuing these advanced materials, we should also look into environmental remediation by using biomass filled materials. As was reported in literature, some dandelion were used, and the cotton as well as cauliflower were used to make electrodes for these supercapacitors. So in conclusions, we've seen that we can actually have a very rational design for making reproducible carbon spheres, and also we can dope them to enhance their performance. And we saw that the PS pen actually created a very large cavity, and CTAP was used as a structure directing agent. And also the hollow carbon spheres on the sheet had a very high specific capacitance of 288 farads per gram. And also the mesoporous carbon spheres which had ionic liquids exhibited 270 farads per gram. And over 70% supercapacitance retention was obtained for hollow carbon spheres on the sheet at a current density of 0.5 ampere per gram in 2 electrode system. I would like to acknowledge Professor Liu, Professor Chen, all ideas, staff and students, University of South Africa, Chin, Zapeng, Wang Wei, Zong, Hebei University of Science and Technology, my family and friends. And I would like to thank you for your attention.
Dr. Ksaba, thank you very much for your interesting presentation. And we actually have a few minutes for questions. So there was a question in chat, which electrolyte for PYCN and SCS? The question in the chat.
Excuse me, can you repeat the question?
Which electrolyte for PYCN and SCS? The question.
Which electrolyte?
Yes, which electrolyte?
The carbon sphere was the electrolyte.
The carbon sphere was the electrolyte. All right.
Oh, sorry, no, sorry, the electrolyte, I'm very sorry. The electrolyte was the potassium hydroxide solution.
Potassium hydroxide solution.
Yes, yes.
So any other questions? Any other questions? So no questions. Thank you very much for today's presentations. Unfortunately, at the beginning we had some technical issues and I had to cut a few minutes some presentations at the beginning. I apologize, but luckily everyone got chance today to make a presentation. All the questions can be asked directly in the personal cabinet or in the chat. And in 8 minutes, there will be the next event is Science Stand-Up Battle. Please stay here, it will start in 8 minutes. This is popularization activity, it is about science and fun. So please stay here, and I have to tell you goodbye for today, and we will meet tomorrow. Thank you, everyone.
I wanna feel oppressed without any rest. I wanna see you sing, I wanna see you fight, 'cause you are the real beauty of human rights. Makes my body dance for ya.
Dear friends, welcome to Science Stand-Up Battle. A few words about this activity. The aim of Science Stand-Up Battle is to speak about your current research in a fun and simple manner. The presentations will be held today and tomorrow at 2 p.m. Moscow time. Please make adjustments for your local time. It should only be based on the speaker's personal research, a maximum of 7 and a minimum of 5 minutes per speaker. The winner will be determined by you, by the viewers. Forum participants can vote using the link BRICS-YSF2020.ru/media. So that's the media section of our website, and there is a tab Science Stand Up. You will be able to start voting tomorrow after 6 p.m. Moscow time. That is after noon Brasilia time, 8:30 p.m. New Delhi time, 11 p.m. Beijing time, and 5 p.m. Pretoria time. So make sure you support the speaker that you like. We have quite a few contestants, actually even more than we had expected, including 3 videos from the hosts who are not members of the official Russian delegation, but they volunteered to take part in this stand-up battle, and the organizers granted their request. So no more talking, it's time to watch now. And our first video is from Arthur Henrique Azevedo Gonçalves from Brazil. Please enjoy.
Hi! Do you know what graphene-like materials are and how it can be used to treat dye effluents? Today, I'll be briefing you how a magnetic composite would be a good alternative to treat dyeing pollution. My name is Arthur Azevedo and I'm a master's student from Rio de Janeiro State University in conjunction with National Institute of Technology from Brazil. Brazil has one of the biggest textile industries in the world and is responsible for developing regions and employing almost 17% of the Brazilian workers of manufacturing industry. Therefore, Brazil is one of the biggest organic dye consumers in the world. You can see the other BRICS countries in this graph. However, it is estimated that 50 liters to 100 liters of effluent are generated for each kilogram of produced fabric. One example of a worldwide used organic dye is indigo carmine. Indigo carmine is an anionic dye with an intense blue color, very used for denim fabrication. Despite of its splendid color, indigo carmine can be environmentally harmful. Besides, indigo carmine is associated with many different health problems, such as cancer. This problem becomes worse due to its high stability when disposed in the environment. Therefore, new technologies are required to discolorate textile dye effluents. Now, do you remember the magnetic graphene-like composite I told you opening this video? What if I tell you that we can rapidly discolorate an indigo carmine dye solution with this material? Besides, that we can recover this material with a magnet to be used in the next batch of indigo carmine effluent. Okay, first things first. With each passing year, the term graphene is gaining more interest in the scientific world. But what exactly are graphene-like materials? Well, graphene can be obtained by the graphite exfoliation, and it's known as the thinnest material due to its carbon atom thick. It is defined as a 2D sheet composed by sp2 hybridized carbons in a hexagonal form like a honeycomb. There are the two interesting graphene-like materials, graphene oxide, GO, and reduced graphene oxide, RGO. The first is oxygen-rich, while RGO is obtained by the reduction of these oxygen groups. Okay, you just said nothing to me. What do all these things matter? It matters because graphene-like materials have excellent electronic, mechanical, and textural properties. Graphene-like materials can form excellent composites with iron oxides, for example. Better yet, Brazil, India, and China are among the countries with the largest reserves of graphite. And why iron oxides? Iron oxides have many interesting properties. Magnetite, for example, is a good semiconductor, has a good biocompatibility, and it's cheaper than titanium, which is a good photocatalyst, for example. And look what coincidence we have here. Our BRICS countries, most of them are iron abundant. That said, the objective in this work was to synthesize magnetic iron oxide particles anchored on RGO sheets, turning this material composite to discolorate indigo carmine dye solution, which is a widely used organic dye in the world. This is possible due to a process known by photophantom process, which generates hydroxyl radicals to attack indigo carmine dye molecule, producing water, CO2, and mineral acids. It is much better for the environment, isn't it? And after all this happened, we still can easily recover the catalyst by approximating a magnet. In this figure, you can see the reactor we used to evaluate the indigo carmine dye discoloration. You can also see here that we used the UV lamp to simulate UV radiation to activate the photocatalyst. Also, we used the ejected reactor to maintain the room temperature. Each liquid we took was analyzed in a UV spectrometer to observe the indigo carmine discoloration. Now, let's jump into our results. X-ray diffraction patterns show that graphite, GO, and RGO are carbon materials, but they are completely different. X-ray diffraction also shows that magnetite particles were formed on RGO sheets. You can see here all these peaks related to magnetite. You can also see this in microscopic analysis. RGO shows a compacted sheet morphology, while the composite has the magnetite particles on RGO sheets. Furthermore, after we synthesized the material, we approximated a magnetic bar to the composite and we observed that the composite was magnetic. This graph here shows the indigo carmine dye discoloration in function of time. We can note that with 5 minutes of reaction, our composite discolorated 100% of indigo carmine dye solution. After the first reaction, we recovered the catalyst with a magnet and reused it in the second cycle. Once again, 5 minutes of reaction were enough to discolorate the indigo carmine dye solution. X-ray photoelectron spectroscopy, which is a surface analysis technique, shows that we have a iron 3 plus, iron 2 plus ratio of 1.9, which means that magnetite particles were preserved even after the first cycle. The excellent performance of this composite can be attributed to the composite narrow band gap. A narrow band gap means that we have an excellent electromobility, which is the key factor for a good photocatalyst. Here is a short video showing that with a simple magnetic bar, we can easily separate our composite from the medium. In conclusion, our results showed that magnetite particles anchored on graphene-like materials would be a promising alternative for the dyeing remediation. Furthermore, our countries are graphite and iron abundant. We can use that in our advantage. So, I hope you guys have enjoyed this video. And when the situation is over, I hope to see you guys here in Brazil. Thank you very much and muito obrigado.
Muito obrigado, Arthur. And now it's time to watch a video from South Africa, from Luis Botha.
Well, hello there. I will be giving a brief introduction into greenhouse gases and how green energy solutions can eliminate the production of greenhouse gases. The population is increasing rapidly. And to keep up with this rapid growth, energy production, industrial production, and transportation has to keep up. This leads to an increase in the production of greenhouse gases and pollution. Now, how does greenhouse gases cause global warming, you say? Greenhouse gases form a dense layer around the planet. Normally, the solar radiation from the sun is reflected back into space. However, due to the dense layer of greenhouse gases, the solar radiation is not reflected into space, but instead gets re-emitted back onto the planet's surface. This causes global warming and climate change. The adverse effects that climate change has on the planet is more notable from observation of nature. One noticeable effect concerns the oceans. In the figure, the increase of pH level in the oceans results in the death of coral reefs. It's important to notice that coral reefs are responsible for housing numerous marine life and oceanic plankton, who are the major producers of oxygen in our atmosphere. The simplest solution to reduce greenhouse gases is by switching over to green energy. Green energy is energy obtained from renewable sources such as solar energy, wind energy, and hydrogen fuel. In hydrogen fuel, water is split into hydrogen and oxygen using electricity, where oxygen is then released into the atmosphere and hydrogen is stored as a fuel. This is conducted by using electrolyzers. On the other hand, energy can be obtained by recombining the hydrogen and the oxygen to form water. This is done using fuel cells. In a fuel cell, as you can see, the hydrogen loses its electron. The electron moves from the anode all the way to the cathode, where it forms with the oxygen and then combines with the hydrogen that is present to form water. However, these fuel cells and electrolyzers are hindered by a large overpotential which is required for the reaction to occur. Not only that, the reaction is also hindered by slow reaction kinetics. To overcome this, electrocatalysis is required, which speeds up the reaction and lowers the overpotentials. Now, in order to overcome these hindrances, a suitable electrocatalyst is required. A suitable electrocatalyst can be designed by using properties of a primary metal, such as platinum, enhancing it with a secondary metal, such as nickel, to make electrocatalyst. Now, these electrocatalysts can then be fine-tuned to be used for other fuel cells, electrolyzers, or both, if it's correctly fine-tuned. There are two types of research that can be performed to get the results. One is from experimental research. Second is from theoretical research. Experimental is using a laboratory, such as Dexter's laboratory, but theoretical is using complex computer simulations to calculate results. Theoretical research is an ideal type of research for studying various properties of materials due to the advantages of using computer simulations, which allows the researcher to narrow down all the possible types of material required as electrocatalysts. This then enables the experimental chemist to take the results, perform it in a laboratory, and then verify the results to obtain suitable electrocatalysts for either fuel cells, electrocatalysts, or both. Therefore, reaching the goal of green energy can be achieved by collaboration between different types of research. It's not limited to experimental or theoretical. There's all kinds of different research fields that can be used. But this is the end of my slide. Thank you very much for listening and have a wonderful day. Goodbye.
Thank you very much, Louise. Thank you. We enjoyed your animations. And our next video is from India, from Sandeep Samvanshi.
Hey, hi. How are you? Why are you looking so nervous?
Hi. I just came from hospital. Doctor told me that I have a cancer.
Oh, but don't be nervous. Nowadays technology is so advanced. So it can be cured.
Yeah. Doctor told me that it can be cured with radiotherapy. But I know it's a lengthy and costly process. Also, it has many side effects such as sickness, hair loss, eye irritation, skin problem, etc.
Yeah, that's true. Radiotherapy has some limitations in cancer treatment. But what about cooking cancer with magnetic nanoparticles and hyperthermia?
What? I didn't understand.
I am talking about magnetic fluid hyperthermia therapy. It is an advanced method based on nanotechnology which has emerged as one of the promising methods for cancer treatment. I am working on this method at my university lab.
Looks interesting to hear. Can you please elaborate it for me?
Yeah. Why not? Basically, in this therapy, magnetic nanoparticles are introduced into the tumor, and then they provide the thermotherapy.
What? Did you say thermotherapy?
Yes. The thermotherapy raises the temperature of the tumor cell while keeping the surrounding healthy tissues at a lower degree of body.
But how these nanoparticles generate the heat?
If we put a magnet near the nanoparticles, they will line up with the magnet. If we want the nanoparticles to move, we can move the magnet and the nanoparticles will follow. If we want the nanoparticles to move quickly, we can use an alternating magnetic field. The nanoparticles follow the magnetic field and move to always align with it. If the alternating magnetic field moves quickly, so will the nanoparticles. When they move quickly, they start getting hotter and hotter. If they are in the body, this can increase the temperature of the cancer tissue around the nanoparticle, which is called hyperthermia. This can be helpful in treating cancer. Let's look at an example. This boy has a tumor, but doctors are going to help him by using magnetic nanoparticle therapy. First, the doctor injects the nanoparticles directly into the tumor. Since the nanoparticles are really small, they move randomly around the cells. Now the doctor puts the tumor in an alternating magnetic field. This makes the nanoparticles move very quickly, and if they move quickly, they will start to get hot. Really hot. The temperature can get so hot that the nanoparticles start to hurt the bad cells, and the tumor can shrink over time.
Oh, I see. you use the magnetic fluids to induce the hyperthermia that raises the tumor temperature.
You were right. We use magnetic fluids. It is a liquid that becomes strongly magnetized in the presence of magnetic field.
You said magnetic nanofluid contains magnetic nanoparticles. So the magnetic nanoparticles, each billionth of a meter in size, can seep into the tissue of the tumor cell.
Yes, this is due to the high permeability of these vessels. Magnetic nanoparticles are really small particles about 1,000 times smaller than a single cell. Thus it is possible to magnetically target these fluids to cancerous tissues intravenously.
Oh. And afterwards these magnetic nanoparticles can be heated by exposing the tumor to an alternating magnetic field.
Yes. This causes the tissue's death by heating. The process is called magnetic fluid hyperthermia.
Which you call thermotherapy.
Exactly. Temperatures in the range of 41 to 45 degrees Celsius are enough to slow or halt the growth of cancerous tissue.
However, these temperatures also destroy healthy cells. So this is your challenge, to use hyperthermia treatment to increase the temperature of tumor cells for about 30 minutes.
Yes. And yet maintain the healthy tissue temperature below 41 degrees Celsius. We also have to pick the right material for the nanoparticles.
Ah. So what material do you choose? Because platinum and nickel can be toxic.
This is really a good question. We are using biocompatible iron oxide nanoparticles which are highly stable and responsive to magnetic field. When we send the nanoparticles into the body, we need to add a coating. It's like a hard shell coating that covers the particles. The coating helps the nanoparticle work correctly without hurting any other healthy cells. If you put a bunch of nanoparticles in your body without a coating, they could all clump together. This would be bad because they could clog an area in your body and not get to the right place. So we add coatings. We need to pick the right kind of coating that help the nanoparticles go to a specific part of the body. In our recent work, we have shown that coating of the nanoparticles enhances the biocompatibility to better extent.
Fascinating. Is this method currently available in the market for treatment?
No. The method is under clinical trials, and hopefully it will be approved very soon.
Thank you very much. I am so glad to have a discussion about this with you. I hope this method will be approved very soon.
Yeah. Hope so. See you soon. Take care. Bye. The global cancer burden is significant and increasing day by day. According to World Health Organization, the cancer burden is estimated to have risen to 18.1 million new cases and 9.6 million deaths in 2018. Predictions suggest that by 2040, there will be more than 29.4 million new cases each year. Cancer productivity losses due to cancer disease are one of the major concerns of the BRICS countries, and it highlights the need for advanced diagnosis and treatment modalities through the development of multifunctional nanomaterials that allow for point-of-care engineering. By eliminating the need for highly specific and costly equipment, this class of diagnostic and therapeutic materials can be easily implemented in the BRICS countries, which could have a massive impact, not just on the health of individuals, but also at economic level. So, let us come together and fight with cancer. Thank you.
Thank you very much, Sandeep. And we have one more video from India. This time it's from Prasenjit Ghosh.
Hello everyone, welcome to my presentation. I am Dr. Prasenjit Ghosh. I have recently completed my PhD from Indian Institute of Technology, Bombay, India. I am a BRICS Young Scientist Fellow, and in today's Science Stand-Up contest, I will be talking about human waste, its concerns and treatment challenges. This is a broad research area and I work on a particular field that I will discuss subsequently. On daily basis, an adult human produces about 100 to 250 grams of feces and 600 ml to 2.6 liter of urine. Feces contains 75% water and 25% solids, whereas urine contains 94% water and remaining solids. It takes about 12 hours to convert food into feces in the 30 feet long gastrointestinal tract in the human body and 9 to 10 hours to produce 2 cups of urine. Now I will discuss what is sewage. It is a mixture of human wastes along with sanitary items, toilet papers, pads and diapers, other waste residues and huge amount of water. There are two important terms, black water and grey water. The black water contains human feces and urine mostly. Grey water contains wastewater generated from wash basins, bathroom sinks, bathtubs, washing machines, etc. Black water contains fecal solids and urine solids, which is huge if we consider waste generated by a community on a daily basis. Hence, we should see poops and urine everywhere, but we don't. Why? Because it gets treated by sewage treatment plants constructed all over the world. Now, why treatment is required at all? Because human feces can contain diarrhea, cholera, typhoid, hepatitis A causing microbes that can contaminate drinking water if disposed untreated, and it can also contaminate crops if these are grown by sewage irrigation. Poor treatment conditions contributes to 10% of the total disease burden worldwide. This pie chart shows the fate of freshwater withdrawals for various purposes worldwide. It can be seen that 8% of consumed freshwater leads to sewage generation. It is worthwhile to mention here that 24% of globally generated sewage is contributed by the BRICS countries only. With respect to Indian scenario, 78% of sewage remains untreated, which is a major concern. So, what are the usage options of feces and urine? While human feces can be used to produce fertilizer and biogas, aged and recycled urine can also act as fertilizer. But treatment is important before such uses. Various treatment options are available, such as chemical, thermal, physical separation, and biological treatment. Biological processes have been found more effective with recovery options of valuable products such as methane, which is a biogas, biofuel, and fertilizer. Human feces has significant economic value. It can produce around $9.5 billion worth fuel, and methane produced from it can generate enough electricity for 18 million households. Various measures have been undertaken to improve sewage treatment worldwide, such as Sustainable Development Goals, which were set by various water regulatory agencies to improve the water quality by the year 2030. In India, Swachh Bharat mission was undertaken, which began with toilet construction as its major focus. Treatment innovations have also been made, which include production of poop briquettes, which has similar energy content as of coal. Innovation of bioelectric toilets have been made that use treated sewage for flushing toilets, and at the same time harvesting power from treatment to illuminate bulbs, which can be used at night. One major implementation of innovative treatment was made in the form of bio toilets in Indian trains, with an aim to create a discharge-free green corridor wherever Indian railway runs. Earlier, what used to happen, suppose you are crossing a road which has a overhead railway bridge and a train is passing at the same time, and suddenly you feel something smelly on your head. By the time you realize, you are on social media. The railway tracks also used to remain very dirty with various colorful poops. Open defecation of human feces has reduced significantly over time due to such innovative implementation. However, there are some treatment challenges. Widely varying solid content in sewage and its composition often reduces the effectiveness of its treatment in the sewage treatment plants. The combined waste stream of feces and urine is also a major problem for treating. Bioelectric toilets are less power efficient. It is difficult to illuminate bulbs of high wattages. The social acceptance of biotoilets is also a major hurdle towards its implementation in India. Antibiotics get released into the environment through human feces, and they lands in water bodies from treated sewage disposed by sewage treatment plants. Certain microbes are evolved that are often immune against multiple drugs. It is a cause of serious concern. This is, however, the proposed field of my research. According to a recent research done in China, fecal matter plumes generated during toilet flushing could spread COVID-19. Hence, it is a new challenge to the scientists. Now you can see the picture of a dog which has just pooped and is thoughtful about the fate of its poops. Thank you.
Well, thank you very much. It's an unusual view of this topic. And one more video from India, from Anupma Thakur.
Hello everyone, people call me Smokey and I love it though. Reason is simple, I make this environment smoking hot. I think of engines in an earth state of mind. Behind the walls of these engines, life is defined. It's all about airborne particles and liquid particulates, oxides of nitrogen, sulfur and carbon. Yo, I'm smoking in an earth state of mind. Cars, scooters and planes are my favorite. And love for you people is always great. Straight out from the hot dungeons of this nature, I'm able to raise the temperature by 1 degree. Yo, I'm smoking in an earth state of mind. To put up a fight against ozone, I never thought I would see that train. Crazy, quiet and beautiful like a plane. When I was young, my enemy had a chain. I was kicked out and without any disdain. Now, it's time. I'm gonna move your son. Yo, it's Smokey in an earth state of mind. But there's a deja vu. That there's a slippery light, quite a bite. I can't take that fatty researcher. I can't take that hydrogen anymore. Damn! This Smokey dream again. I'm sick of it. The Smokey anthem is really troubling me a lot. People think of their favorite foods, adventurous places, and even new adventures like paragliding. But I think of the Smokey and hydrogen all the time. Yes, I'm talking about hydrogen, the greatest weapon that we have in our armory. This hydrogen can not only defeat Smokey, but also provide us with the clean future fuel. Yes, come on, I'll show you how this actually happens. This is the photoelectrochemical cell in which the water is getting split into hydrogen and oxygen in the presence of the solar light. Now, I will briefly explain by telling a tale of two friends. Those are photons and the cunning anode, who are very jealous of the strong chemical friendship bond that exists between the oxygen and hydrogen molecule of water. Now this very smart and cunning anode plans a conspiracy in which it utilizes the photons, which are basically the carrier of electromagnetic energy from the sun. So when these photons falls at the surface of this anode, the electron hole pair formation takes place. And then this anode, without wasting any time, surpasses all these electrons via super fast tunnel to this cathode. And then the holes which are left behind at the surface of this electrode participate in water oxidation reaction. And this hydrogen here has a strong and passionate love towards electrons, gets attracted to the cathode, and the oxygen ion, which does not at all like electrons, stay back at the anode and combines with holes to produce oxygen gas at the surface of this electrode. While the hydrogen ions which are formed gets collected at the cathode, attains all these electrons and form hydrogen molecule as a product at this electrode. Now this basic principle solves as the mechanism for photoelectrochemical cells being used today. And now the actual question is that will these oxygen and hydrogen ion ever meet again? Will they form water again? And the answer to this question is yes, they will one day definitely meet when we will utilize the stored hydrogen as a carrier, as a fuel, as a clean fuel in vehicles. And when this hydrogen will be used as fuel, it will combine with the oxygen molecule from the air to form water as a product and produce huge amount of energy. And this hydrogen is the only solution that we have to kill and destroy the evil objectives of smoking. And now, let's salute to the long-lost friendship of this hydrogen and oxygen. At the end, I would like to say thank you. I'm Anupama Thakur, the faculty researcher, signing off.
Well, thank you very much, Smokey. That was fun. Our next video is from China, and it's from Wan Hansang.
Hi, I'm Han Yang from GI. GI is a technology company headquartered in Beijing, and we are focusing on AI, including computer vision, and we are also making fully autonomous drones. Today, I will show you a short documentary about how we are helping one of the largest Chinese animal conservation group, CFCA, to protect the Chinese south leopard in Shanxi province. Please enjoy.
华北豹是唯一只生活在中国的一种豹子，我们是它们在这个星球上唯一的邻居。野外的华北豹现在已经非常稀少，我们最不希望的就是这种美丽的豹子，像华南虎一样在野外消失。我们这个团队叫猫盟。 是一个中国本土的这个野生动物保护的机构。那么我们在山西这个地方呢，在这儿已经来了断断续续来了有10年了吧。他那边相机就在这儿。你看这个拍的是个狗獾。从13年到14年，就是我们的队员加上北京师范大学的这个科学家，我们一起在这儿工作。当时有4、5个人吧，大概花了有整整1年的时间吧，布置了大概200多平方公里的这个范围啊。当时相机大概已经布下去70、80台吧，一直到2018年，现在是接近500平方公里的这个监测范围。那么相机呢，大概是100台左右。这个就是红外感应器。 这个是触发那一部分是吗？对，这是触发，这是拍摄，这是红外照明。这地方特别亮，你看过来，这地方正好太阳形成一个光斑，形成一个强烈的热对比，所以它就会触发。有时候我们装相机它基本上是没法避免的。一段视频，比如说拍15秒，它一个相机有时候一下子就拍了可能好几百段。所以我们在任何一个地方，我们说我们要监测这儿，至少我们要花半年到1年的时间。 才能把这儿的这个动物的情况基本上做到心中有数。
我以前是做动物行为学研究的，来到猫盟之后呢，有80%的时间大概都花在看数据上边了。先把这数据用电脑一张一张的看，或者是一段视频一段视频的看，看了之后把它按物种分了文件夹，再把它整到Excel表格里面。 然后再计数，计完数之后出图，整个过程差不多，怎么着都得1个星期了。
我们泛华智能和猫盟合作半年了，但是这半年里面又不知道多少动物就没了，这个，所以在我看来，有一些工作就不应该人去做，比如看照片这种工作，你人的工作应该是放到更宝贵的事情上，比如上山去收集数据。所以我们一直认为这些看照片的工作应该让计算机视觉去做，让电脑自动帮人把这所有工作全部完成。
所以后来就是跟 GI 跟泛华智能的汉阳我们认识了以后，他一说这个，哎，我就觉得特别好。我说这个东西可以极大的解放我们的这个生产力。
所以我们做的就是把基础软件提供给他们，他们基于我们的软件训练出自己合适的模型，来识别他们想要识别的物种。
我现在呢，把我的经验和知识交给电脑，就能够在1、2个小时之内处理过去我需要1个星期才能完成的数据处理这种工作量。
当下凡那边能够更高效地处理完所有的数据，我们也就能够更及时地获取这儿的山里面野生动物它现在的状况。那么这意味着我们的保护会更加高效，我们能够更好地保护这儿的这些野生动物。
Thank you very much. We really enjoyed the nature that you have shown us. We are actually halfway through our videos today. And now it's a video from Russia, from Yevgeny Alexandrov.
Hello everyone, I am Yevgeny Alexandrov from Samara, Russia. And Samara is located in the breast of Russia. Therefore, it can be called the heart of Russia. and the shape of Samara region looks like heart. Samara is famous by producing rocket engines and by oil industry. Today I want to talk about how artificial intelligence and new materials help us save the planet. You know that greenhouse gas affects the climate change on Earth. For example, it produces greenhouse effect, and this heats up our planet. I think many of you feels the change of climate. For example, this winter in Samara was very snowy, and my daughter was able to dig a cave in snow hills. Another problem is radioactive contamination, which can destroy all life on the Earth. And cancerogens are produced by many industrial companies. These compounds destroy our genes and cause cancer. But what are the solutions of these problems? Maybe we can move to another planet, but I think not in the nearest time. Science gives us very good opportunities for solving these problems. For example, science gives us new sponge-like materials, which were discovered very recently. And these materials have a very perfect order because they are crystalline, and they have also very nice cavities. And these cavities are very small, and at the same time they have very large surface area. 1 gram of such compound, such crystals, can have the surface area equivalent to the football field. Because of these cavities, these materials can capture CO2, which is the main part of greenhouse gas. They also can capture radioactive iodine, and they can capture cancerogens. For example, they can clean up water from dichromate anions in minutes. At the same time, we have very big question. There are so much porous materials, but which of them are the best for given application? And to answer this question, we use special tools, theoretical tools, because it is impossible to synthesize all these materials and check their properties in lab. And we make classification of already known properties of these materials to make prediction of unknown properties. For example, we have a porous material, and this material can have triangular or rectangular pores, and these pores can be constructed by building blocks of different geometry, diagonal, prismatic, square, or octahedron. And many different chemicals can have such geometries. This kind of collaborations compose the knowledge base. Knowledge base is a part of expert system, and expert system have books, brains, and language for communication with the user. And user can ask expert system, what is the best material for this kind of application? And expert system can, before answering, it can ask again, what do you mean exactly? What kind of details can you provide me more? For example, what kind of pores do you consider? And so on. And after clarification of these questions, inference engine can produce new hypothetical structures and also give the list of the best materials which are already synthesized before. This is what we do in our research work. We create decision trees, we predict new materials, and make simulation of these materials using our program package installed on the supercomputer. And after this, we go to lab for making synthesis. That's all. Thank you for your attention.
Thank you very much. Just a reminder, tomorrow you'll be able to vote for the ones that you like, for the videos that you like. And now we continue with one more video from Russia, from Ivan Fedosov.
Hello, dear colleagues. My name is Ivan Fedosov. I am a second-year postgraduate at South Ural State University. My area of interest is development of measurement technique and data processing. Today I will tell you how to determine that you are you. Wait, it's too easy. Today I will tell you how to determine that you are you if you're not a person, but a measuring device, for example, a temperature sensor. Imagine a situation. You live, walk and feel all symptoms of the disease. You have headache, fever, arms and legs ache. You take your new electronic thermometer, measure your temperature and see 36.6. I don't believe it. You find another electronic thermometer, measure your temperature elsewhere and see 36.5. You don't believe it, shout you. Try to find your old mercury thermometer. It shows 39. Wow, you are sick. To be precise, you confirmed you are you because your electronic thermometer is also sick. Unlike humans, measuring devices or sensors have a strictly defined function to measure flow rate, pressure, or temperature. At the same time, sensors don't have additional sensations. However, like humans, sensors sometimes get sick, and it is very bad because measurement errors come at a price in industry. For example, in 2019, casting industry lost around the world about 2% of the volume due to temperature measurement error. Look at this value, $315 million. In addition to economic losses, incorrect measurement of process parameters can lead to technical accidents and human casualties. Our goal is to help sensors to determine their aches and to tell about it. Today we have focused on temperature sensors as they take up to 50% of all sensors in industry. Industrial temperature sensors are electronic devices that consist of primary transducer and electronic unit. The primary transducer consists of special selected metals which properties vary with temperature. The electronic unit digitizes these properties and convert it in temperature. The most common solution for improving reliability of temperature sensors is to duplicate them. To do this, we placed the second temperature sensors near to first one. However, the second sensor doesn't guarantee that it will be able to determine in time that the first sensor is sick. Also, the second sensor may get sick before the first sensor, and moreover, they both may get sick together. How have we led the sensor to tell us more about its state? The first method is similar to work of a fitness tracker. We can trace our pulse continuously by themselves, but we can use fitness tracker for this goal. The main question in this approach is how to find a pulse signal from many other signals of the human body. For example, some fitness tracker can find even cucumber pulse. Trust me, I've checked it. So, in the first option, we add another metal to the primary transducer of the sensor, whose properties also dependent on the temperature. It allows us getting an additional information about sensor. Then we extract information about the state of the sensor by our algorithms, determine the current diagnosis of the sensor, and the remaining time of its trouble-free operation. In another way, we predict the death time of the sensor. The main difficulty of its method is how to extract information from modified sensor design. We have learned to do this. The second method is similar to choose a watermelon, as it happens in Russia. You come to the market, choose a beautiful watermelon, knock on it, and try to hear something. The main questions in this method: where should you knock, on the watermelon or on the head? And how do you interpret the sound heard from watermelon to choose a? Seriously though, it looks like this. We send test current signal to the primary transducer of the sensor and receive a response containing additional information. Then we extract information by our algorithms, determine the current diagnosis of the sensor and the remaining time of trouble-free operation. The main difficulty of this method is how to acquire the response and extract additional information from response. We have learned to do this. Today, our project is 2.5 years old. During this time, we have conducted more than 1,000 hours of testing, and we have developed 2 prototypes that are able to determine their state. In addition, we represent the real demands of industry in our products. We are negotiating with some companies from production aircraft engine components to production of automobile tires. Sensors, they are almost like people, and also they sometimes get sick. Our mission is to help sensors to determine their state and to tell about it. However, our technology is not widespread yet, so if you feel bad and the thermometer shows 36.6, you should consult a doctor. Thanks.
Thank you, Ivan. I hope nobody feels sick. I hope everybody feels fine. And our next video is from India, from Nishant Kumar.
Good morning, everybody. I'm Nishant Kumar, Early Doc Research Fellow at Indian Institute of Technology, Delhi. I am from India, and today I am going to present my project work. This project work is totally based on the artificial neural network based control techniques, and this control technique has used for the solar PV energy generation system utilization improvement. Means that here the utilization factor of the solar PV energy generations will improve by using this artificial neural network based control technique. In this project, this type of solar network has considered. Means I have used one solar panel for extraction of solar energy from the sun, as well as the generated solar energy we will use for the all the local loads and household loads, and after that all the extra power will be fed to the grid. And in some cases, suppose our load demand is high, then on that situations we will take the extra energy from the grid to match the load or local loads. It's like this type of system has considered, but the problem with this system is this network will only use for the 8 to 9 hours, because sun will available only for 8 AM to 5 PM like this, so it will work mainly for 8 to 9 hours. The question is, what is the use of this entire network during the night time? Means night time means 5 PM to 7 PM, around 15 to 16 hours. This entire solar network is totally useless. Means that because in night time the power will directly come from the grid and used for all the loads. But what is the use of this solar circuit? Solar circuit in general looks like this. In this circuit we can see that a solar circuit is consists of 1 or 2 converters. Mainly for we will use 2 converters, means that one converter for the power extraction from the panel and another converter for extracted power conversions into AC. And then because all our local loads are in general AC in nature, so this DC to AC conversions we use one converter. But question is, this system will work only in the daytime, but in the what is the use of this entire circuit in the night time? In night time, both converter and capacitors and filters and all interfacing inductors all will be useless. Only the power will come through the grid and go to the So we can conclude that the entire solar network or solar system will be useless during the night time, and in night time is around 2/3 of the whole day. So the utilization factor of this entire electrical network or entire solar network will be useless for 1/3 of the time. So how we can improve this system, or how we can use this network for some other purpose? This is the key objective of this whole project. So here in this project, I have developed a new technique for operate this electrical network in night time also for some other purpose. Here mainly this network will be used during night time for reactive power generations, because for reactive power generation required only two things. One is a converter, which is here, and another is here the capacitor which is on the DC link. So this capacitor and converter can use during the night time for reactive power generations. I know during the night solar power will not available, so solar active power generation by using the solar panel is not possible, but this at least some portion of this electrical network can use for some other purpose, and the purpose is reactive power generation during the night time. And we know that all AC loads require two type of energy. Some part of energy is active power and some is reactive power, and both combinedly required for any AC load. So the reactive power will generate by using this network, and the active power only will come from the grid. So both electrical network and grid will fulfill the load demand. So here I can conclude that this network will operate during the night time for reactive power generation, which will support the grid in the terms of reactive power generations. So the burden on the grid will lesser during night for fulfill the reactive power load demand. For that purpose, this control I have developed. In this control, I have used the artificial neural network, which is based on ANOVA kernel least mean square algorithm. And in this control, this neural network techniques mainly for the estimation purpose. And this estimates the active and reactive power requirement of the load, as well as unit temperature generations, which has uses for the synchronization with grid. So this ANOVA kernel here works for two purposes. One for the load power estimation, and another is the grid synchronization. This is the electrical network of this artificial neural network, where I have shown the weight updating process, how this updating process is happening. During this updation process, the data is circulating from input to output side, and as well as input is coming from the load current. This is the entire block diagram of the neural network which I have used. This is totally based on the single layer neurons, and this is the all mathematics in the block format I have shown here. This is the experimental setup which I have used during my testing. What algorithm I have tested for testing purpose. This is the experimental setup on which I have developed. The obtained results are shown here. In these results, we can see that the 1.82 kilowatt power is going into the grid, and the load demand 1.92 kilowatt power is going to the load. And these results I have obtained during the daytime. Here day to night mode of operation is shown, means that during evening time how the system will work, means during the daytime the PV is generating power, but in night time the PV power is zero, but still the power is coming, means in the night time the power is coming from the grid and going to the load. Here it shows that during the night time the power is coming from the grid, but the reactive power requirement of the load is generated by our circuit. So this is shown here. But in the daytime, the both reactive power and active power is generated by the electrical network, as a solar network, and the daytime the only generated extra power is going inside the grid. Similar type of result is shown into the night to day mode of operation, means in morning time how the system will operate, means in night the solar power is zero, only the grid power is coming and going to the grid. Similarly here during the night time reactive powers is shown and then going to the grid. Similarly, the same operation has shown tested in different type of other conditions also, means the linear load unbalancing conditions, over voltage grid conditions, voltage grid conditions, as well as the grid voltage unbalanced conditions also I have considered for the testing. And this has also shown that 32% unbalance in the grid voltage, but current is totally balanced, and like this. So that I conclude that the AI-based developed technique for the solar is highly suitable, as well as it improves the overall performance of the electrical network, as well as utilization factor of the electrical network also improved by using this AI-based control technique. Thank you for your kind attention. Thank you everyone.
Thank you very much, Nishant, for your video. I have information from our technical team. It's a request to all the participants who are presenting tomorrow. Please join 1 hour before the beginning of the forum, because we need to check your presentations, which will take up to 10 minutes. After that, you can leave and join any time. Thank you very much. We have 3 more videos to go today, and this one is from China by Liu Yang.
Hello everyone. Today we are going to briefly introduce a new matrix product named as semi-tensor product or matrix, and how it is applied to the researches of BRICS networks and gene networks. We firstly see 2 simple examples of matrix product. For example, given matrix A with dimension 2 times 2 and matrix B with dimension 2 times 2. Then under the general matrix product, we can obtain its product is this 2 times 2 matrix. However, if matrix B is a row vector, it is not well defined for the matrix product of matrix A and B. So how can we define the matrix product for this example? So let's see what is semi-tensor product of matrix. Semi-tensor product of matrix is defined based on the chronic product of matrix. The chronic product of matrix is defined as this equation in definition 1, which extends the dimension of A and B. Then we see the concept of semi-tensor product of matrix, which is actually the generalization of common matrix product, because under the semi-tensor product of matrix, we can product 2 matrices with arbitrary dimensions. Here we no longer need set n equals p, and we can also see that where n equals p, the semi-tensor product of matrix is actually the well-known general matrix product. For example, given a 3 times 3 matrix A and a 2 times 2 matrix B, it is invisible under general matrix product. However, it is well defined under the semi-tensor product of matrix, and its final product is actually a 6 times 6 matrix. Note that BRICS networks is a network where nodes are connected with logical operators. For example, the negation operator, conjunction operator, disjunction operator, conditional operator, and the biconditional operator. The detailed truth table for these logical operators are shown in this table. For example, given p equals 1, its negation is 0. Logical function is a function with several logical variables x1, x2 to xn, and each logical variables are joined by logical operators like negation, conjunction, and so on. This is a simple example for a logical function with 3 variables pqr. Then, before we learn how to apply the semi-tensor product of matrix to BRICS networks, we define an equivalence between logical variable 1, 0, and the vectors del2, 1, and del2, 2. This means we define an equivalence for the logical domain to the vector set delta. Under this equivalence, any logical function can be equivalently expressed by an attribute matrix form. Then we can find a unique structure matrix for any logical operators. For example, as for the negation operator, we can find the matrix Mn, and a conjunction operator, we can find matrix Mc, and so on. So the logical expression, we can express it into matrix form. Under the equivalence between the logical expression and its matrix form, we can now study the logical dynamics of BRICS networks under the matrix form. As for BRICS networks, By expressing the logical variables using vectors, we can finally express the logical dynamics of brain networks under the matrix form. xt plus 1 equals to matrix L times xt. xt is the subtensor product of x1 to xn. And as for Boolean control networks, where some external control inputs are added in Boolean networks, one can also find the matrix form xt plus 1 equals to matrix L times ut times xt. Here, matrix L is called the state transition matrix, describing the whole state space. For example, consider a Boolean network with 3 nodes A, B, C. The logical connection between these nodes are given by these functions. So we can find a unique matrix L with dimension 8 times 8, which uniquely describes the state space, how the logical states update. It is well known that the dynamics of T-cell can be modeled by Boolean networks with 19 nodes. In the research of drug treatments in curing cancers, one needs to regulate the dynamics of T-cell into a stable configuration. Now, let's see how to regulate the dynamics of T-cell using the subtensor product of matrix. The T-cell has 9 nodes, and this is a network structure, how the genes are connected with each other. Using control design, we can regulate 15 gene nodes and design the controllers. We can finally regulate T-cell from non-stable dynamics to a stable dynamics. See, before control, there are many cycles and fixed points. However, after control, there only exists one fixed point. This control method is very efficient, and we can find how to regulate T-cell to a stable dynamic. Recently, many fundamental works have been obtained under the matrix framework. xt plus 1 equals matrix L times xt, such as the topics of synchronization, observability, disturbance decoupling, game theory, function perturbation, and so on. These are some fundamental references on the researches of Boolean networks using the subtensor product of matrix. In the end, I wish the conference great success and wish all of you success in your work and happiness to your life. And welcome to visiting Zhejiang Normal University, Jinhua, China. Thanks.
Thank you very much. We have one more video from Russia by Sergei Pavlov.
Come here. My name is Sergei, and what do you think this is? It's sugar, yes, but for me it's primarily a crystal. As you may know, crystals are found everywhere around us. For example, precious stones, which we stick in the jewelry, are crystals. Crystals also may be found in phones, computers, telescopes, mechanical watches. Rubies are used for mechanical watches, and this is how untreated ruby that we grew looks like. We are material scientists, but we're also partially alchemists. But unlike them, we can create materials with the required properties for science and technology. With rubies and sapphires, for example, we can control color and growth parameters. Color, which is associated with concentration of chromium, determines the mechanical and optical properties. Mechanical properties are extremely important, for example, in watchstones. And optical properties are important in laser technology. Color and size are of course fun and interesting, but our team is interested in more subtle matters. So we have focused our attention on the world's top subject ferrites. Due to their unique crystal structure, they have uniquely high anisotropy, and these materials can be used in microwave electronics. The management of such subtle matters is the top class of material science, and already we have achieved significant success in this field. For the first time in the world, we have achieved 50% substitution of iron atoms with the aluminum while preserving the initial type of crystal structure. So we've got the material with this chemical formula. And already we can vary the ferromagnetic resonance of barium hexaferrite in the more than 100 GHz frequency range. And for the first time in the world, we have created a new type of ferrite with this chemical formula. And we call it the V-type ferrite. All this is possible due to cationic substitution of iron atoms in the hexaferrite structure with aluminum or titanium atoms, with magnetic moments and ionic radiuses different from iron. This ensures that the integral properties of the material can be tuned. For example, substituting just 2 of the 12 iron atoms with aluminum shifts the frequency of ferromagnetic resonance from 50 GHz to 100, while substituting them with titanium lowers the frequency to 5 GHz. All these changes are happening due to differences in size and magnetic moments between iron and replacement cations. The crystal lattice is distorted, and consequently the anisotropy of the crystal changes as well. Also, if you use, for example, thin plates of ferrite single crystal, in addition to the dopant concentration, you can choose the required crystallographic plane and direction, which gives us an additional option for fine material tuning. The material developed by us is promising for creating anechoic chambers for high-precision measurements, composite materials for use in the medicine, and gas sensors. Customizable materials are the future. Customize your materials, create your future.
Well, thank you, Sergey. And we have one more video, the last video for today. It's a different format from the Science Stand-Up, but the guys from Penza State University really wanted to share with you their love for their campus. So please enjoy this video by Sergey Sorokin from Russia.
Dear colleagues and friends from Russia, Brazil, India, China, South Africa and other countries. It's a great honor for me to welcome you all from Russia during this 5th BRICS Young Scientist Forum. My name is Sergey Sorokin, and I am the one of those Russian scientists who are currently working on big data and artificial intelligence. I was born and raised in my hometown called Penza. Even though many of you know only 2 Russian cities, I mean Moscow and St. Petersburg, there are a lot more other interesting cities in Russia, and Penza is one of them. Actually, Penza is a very beautiful city. It is not too far away from Moscow, and I'm very proud to live here. And now we are on Penza State University campus. Penza State University was founded in 1943, and it is the largest university in Penza region. After my 2nd year of studying at Penza State University, I had been invited to one of the best scientific groups in Penza, working on intellectual image processing. I was 19 years old back then, and I had been programming for 2 years by this time. My first supervisor was a full professor named Mikhail Alexandrovich Sherbakov from Penza State University. And I'm really grateful for everything he has done for me. He really had helped me a lot in the beginning of my scientific path. And only now I can fully understand how important the first professor can be. I am sure you will agree with me that science people are very sensitive and vulnerable. That is why they can be easily insulted, and any accident can simply destroy their possible career in science. Nevertheless, let me continue my story. Working really hard day by day, I became a small part of a large scientific community in Russia. And I am really happy to have been working as a scientist from that moment, to have been working with prominent Russian scientists. My scientific interests include deep learning and image processing using machine learning. I am also working with big data, especially how we can correctly use big data for prediction. I am sure we will have a lot of time to discuss this in more detail during our forum. What I would like to underscore is that even in Russian relatively small city, you can do a really good research. I am happy to mention that here in Russia we have practically no restrictions on the access to the internet, and our access to international scientific databases is fully granted. For example, now I am working with my colleagues from Hong Kong University of Science and Technology, and we are doing a great job together. Of course, because of COVID-19, we have to avoid real meetings, and we have to use Skype and other software for communications. But sooner or later, we will definitely find a way to properly cure this disease and to prevent its spreading. But for the meantime, we will do our best as a science community. It looks like our little video journey has come to an end. I hope one day we meet each other in Russia and have a good meal together. I wish you all a successful and productive forum. Thank you very much for your attention and stay safe.
Thank you very much. That was our last video for today. Just a reminder, please vote for the Science Stand-Up performance that you enjoyed most of all in the Media tab at the forum website. You will be able to do so tomorrow starting at 6 p.m. Moscow time. If any of the participants of our forum have not sent in their presentation yet, please do so today. And well, let's call it a day. Thank you very much for your attention. Tomorrow we start as usual at 2 p.m. Moscow time. That means 8 a.m. Brasilia time, 4:30 p.m. New Delhi time, 7 p.m. Beijing time, and 1 p.m. Pretoria time. See you tomorrow.